Good? All right, thank you. Huh?
It's just so all the upward moving, all of that's going to be from this first one, from T1. So we know that the y component of T1. So let's call. So if we say that this vector here. Draw this diagram. It's just confusing. So let's choose a line. So I have this. So we have this vector here, which is T1. Right? We need to figure out what that is. And then we have the other vector, which is its y component. We call this T1 sub y. And then, of course, it has an x component to it. I'll do that. Let's see. Do that in red. And this is, once again, this is just breaking up a force into its component vectors. Vector force into its x and y components, which we've been doing in the last. These are just trigonometry factors, right? And so we can actually now visually see this is T's x, this T sub 1 sub. Oh, and I forgot to give you an important part of this problem that you needed to know before solving it. That the angle that the first wire forms with the ceiling, this is 30 degrees. So if that is 30 degrees, we also know that this is a parallel line to this. This is 30 degrees. This is also 30 degrees, right? This angle right here is also 30 degrees. And that's from our, we know about parallel lines and alternate interior angles. We could have done it the other way. We could have figured out, we could have said that, this angle is 30 degrees, this angle is 60 degrees, this is right angle, so it's also 30. That's just a few geometry. But anyway, we know that this angle is 30 degrees. So what's its y component? Well, the y component, let's see, what involves the hypotenuse and the opposite side? Let me write something. This is really just trigonometry. So Pachola in blood red. So what involves the opposite and the hypotenuse? So opposite and hypotenuse. So that we know the sine of 30 degrees is equal to T1 sub y over the tension in the string going in this direction. So if we solve for T1 sub y, we get T1 sine 30 degrees is equal to T1 sub y. Right? And what did we just say before we kind of dived into the math? We said all the lifting on this point, all of the lifting on that point is being done by the y component of T1. Because T2 is not doing any lifting up or down. It's only pulling to the left. Right? So the entire component that's keeping this object up, keeping it from falling, is the y component of this tension vector. So that has to equal the force of gravity pulling down. So this has to equal the force of gravity. That has to equal this, or this point. So that's 100 newtons. Now, I really want to hit this point home there, because it might be a little confusing to you. We just said this point is stationary. It's not moving up or down. It's not accelerating up or down. And so we know that there's a downward force of 100 newtons. So there must be an upward force that's being provided by these two wires. This wire is providing no upward force. So all of the upward force must be the y component, or the upward component of this force vector on the first wire. So given that, we can now solve for the tension in this first wire, because we have T1. What's sine of 30? Sine of 30 degrees, in case you haven't memorized it, sine of 30 degrees is 1/2. So T1 times 1/2 is equal to 100 newtons. Divide both sides by 1/2, we get T1 is equal to 200 newtons. T1 is equal to 200 newtons. So now we got to figure out what the tension in this second wire is. And we also, there's another clue here. This point isn't moving left or right, it's stationary. So we know that whatever the tension in this wire must be, it must be being offset by a tension or some other force in the opposite direction. And that force in the opposite direction is the x component of the first wire's tension. So it's this, right? So T2 is equal to the x component of the first wire's tension. And what's the x component? Well, it's going to be the tension in the first wire, 200 newtons, times the cosine of 30 degrees, right? It's adjacent over hypotenuse. And that's square root of 3 over 2. So it's 200 square root of 3 over 2, which equals 100 square root of 3 tension in this wire is 100 square roots of 3, which completely offsets it's to the left, and the x component of this wire is 100 square roots of 3 newtons to the right. So that indicates. See the next video. Welcome back. We'll now do another tension problem. And this one is just a slight increment harder than the previous one, just because we have to take out slightly more sophisticated algebra tools than we did in the last one. But it's not really any harder. But you should actually see this one. You should probably see it on the exam. So let's figure out the tension in the wire. So first of all, we know that this point right here is equal to 8. So the tension in this little small wire right here is easy. It's trivial. It's the force of gravity is pulling down at this point at 10 newtons, right? This weight here. And of course, since this point is stationary, the tension in this wire has to be 10 newtons. That's an easy one. So let's just figure out the tension in these two slightly more difficult wires to figure out the tensions of. So once again, we know that this point right here, this point is not accelerating in any direction, right? It's not accelerating in the x direction, nor is it accelerating in the vertical direction or the y direction. So we know that the net forces in the x direction need to be 0 on it, and we know that the net forces in the y direction need to be 0, right? So what are the net forces in the x direction? Well, they're going to be the x components of these two of the tension vectors of both of these wires. So let's draw the tension vectors of the two wires. So this T1 is pulling, tension vector pulls in the direction of the wire along the same line. So let's say that this is the tension vector of T1. If that's the tension vector, its x component would be this. It's a bit of a straight line, but that would be its x component. And its x component, let's see, this is 30 degrees. This is 30 degrees right here. And hopefully this is a bit second nature to you. What is, if this value up here is T1, what is the value of the x component? It's T1 cosine of 30 degrees. T1 cosine of 30 degrees. And you can do your SOHCAHTOA, cosine is adjacent over hypotenuse, right? So the cosine of 30 degrees is equal to this over T1 is equal to the x component over T1. Multiply both sides by T1, you get this. This should be a little bit of second nature right now. The x component is going to be the cosine of the angle between the hypotenuse and the x component times the hypotenuse. And similarly, the x component here would be this first vector. So this is T2. That's T2. This would be its x component. And very similarly, this is 60 degrees. So this would be T2 cosine of 60. Now, what do we know about these two vectors? We know that that their net force is 0, or that you also know that the magnitude of these two vectors should cancel each other out, or that they're equal. I mean, they're pulling in opposite directions. That's pretty obvious. But and so you know that their magnitudes need to be equal. So we know that T1 cosine of 30 is going to equal T2 cosine of 60. So let's write that down. T1 cosine of 30 degrees is equal to T2 cosine of 60. And then we could bring the T2 onto this side. And actually, let's also, I'm trying to save as much space as possible, so I'm guessing this is going to take up a lot of room as well. What's the cosine of 30 degrees? If you haven't memorized it already, square root of 3 over 2. So this becomes square root 3 over 2 times T1. Right? This is the cosine of 30 degrees. And I'm going to bring this onto this side. So cosine of 60 degrees, the cosine of 60 degrees is actually 1/2. Use your calculator if you forgot that. So this is 1/2 T2. Bring it on this side, so it becomes minus 1/2. I'm skipping more steps than normal just because of Too much space. But if you've seen the other videos, I'm not creating too many gaps. This is relatively easy. So we have the square root of 3 times t1 minus 1/2 t2 is equal. So that gives us an equation, one equation, two unknowns. So it doesn't help us much so far, but let's square that away. I'm feeling this will be useful. Now what's going to be happening on the y components? So let's say this is the y component of t1. This is the y component of t2. What do we know? What do we know about the two y components? I could have drawn them here too, and there's shifting over to the left and right. We know that their combined pull upwards, the combined pull of the two vertical tension points, have to offset the force of gravity, right? Pulling down because this point is stationary. So we know these two y components, when you add them together, have the combined tension in the vertical direction just to be 10 newtons, right? It's offsetting this force of gravity. So what's this y component? Well, somewhere that this was t1 cosine of 30, this should start to become a little second nature to you. This is t1 sine of 30, this y component right here. So t1 sine 30 degrees plus this vector, which is t2 sine of 60 degrees. Sine of 60. You can review your trigonometry in your subject. That tends to be, frankly, I think, what just seeing what people get confused on is the trigonometry. But you can review the trig modules, maybe some of the earlier force factor models again. These will make sense. And these will equal 10 newtons. And let's rewrite this up here where I substitute values. So what's the sine of 30? Actually, let me. What's the sine of 30 degrees? The sine of 30 degrees is 1/2. 1/2 t1 plus the sine of 60 degrees, which is square root of 3 over 2. Square root of 3 over 2 t2 is equal to 10. And I don't like this, all these 2's and these 1/2. It's 1/2 here. So let's multiply this whole equation by 2. So 2 times 1/2 is t1 plus square root of 3 t2 is equal to 2 times 10 is square. So let's take this equation up here and let's multiply this equation by 2 and bring it down here. So this original one. So if we multiply this whole thing by 2, how we're doing this other side. So if you multiply square root of 3 over 2 times 2, I'm just doing this here with the 2's in the name. So you get square root of 3 t1 minus t2 is equal to 0, right? Because 0 times 2 is 0. And let's see what we can do. What if we take this top equation? Because we want to start canceling out some terms. Let's take this top equation and multiply it. Let's multiply it by, oh, I don't know, minus, let's multiply it by the square root of 3. So you get square root of 3 t1, right? I'm taking this top equation multiplied by square root of 3. This is just a system of equations. So, and the square root of 3 times this right here. Square root of 3 times square root of 3 is 3. So plus 3 t2 is equal to 20 square root of 3. And now what I want to do is let's I know I'm doing a lot of the equation manipulation here. This is just hopefully a review of algebra 40. Let's subtract this equation from this equation, right? So you can also do it as multiplying by -1 and 2. So when you subtract this from this, these two terms cancel out, right? It's the same. So then you're left with minus t2 from here, minus this, minus 3 t2 is equal to 0 minus 20 square roots of 3. So this becomes minus 4 t2 is equal to minus 20 square roots of 3. And that both sides by minus 4, you get t2 is equal to 5 square roots of 3. So newtons. So that's the tension of this wire. And now we can substitute to figure out t1. So let's do it. Let's use this one right here. It's suitably simple. So we have square root of 3 times t1 minus t2. Well, t2 is 5 square roots of 3, right? 5 square roots of 3 is equal to 0. So we have the square root of 3 t1 is equal to 5 square roots of 3. Divide both sides by square root of 3. You get the tension in the first wire is equal to 5 newtons. So this is pulling with a force of, or tension of 5 newtons, or force. And this is pulling the second wire with a tension of 5 square roots of 3. So this wire right here is actually doing more of the pulling. It's actually more of the force of gravity is ending on this wire. And that makes sense because it's steeper. So since it's steeper, it's contributing more to the y component. It's good whenever you do these problems to kind of do a reality check, just to make sure your numbers make sense. And if you think about their combined tension is something more than 10 newtons. And that makes sense because some of the force that they're pulling with is wasted against pulling each other in the horizontal direction. And I'll see y'all in the next video. Welcome back. We just finished this problem with the pulleys and the inclined plane. I just wanted to do one final thing on this problem just because I think it's interesting. Then we can move on to what seems like a pretty fun problem. So the last thing I want to figure out is we figured out this 20 kilograms, actually the whole system will accelerate up and to the right at 4.13 meters per second squared. Now the second part of this question is, what is the tension? What is the tension in this rope or this wire? And at first you might say, oh, this is complicated, this thing isn't static anymore. The thing is actually accelerating. How do I do it? This is how you think about it. Just pick one part of the system. Let's say that all we could see was this 20 kilogram mass, right? So let's say all we could see was this 20 kilogram mass. And we know it's suspended from a wire. And we also know that this 20 kilogram mass is not accelerating as fast as it would if the wire wasn't there. It's accelerating only at 4.13 meters per second. If the wire wasn't there, it'd be accelerating at 9.8 meters per second, which is acceleration of gravity. So the wire must be exerting some upward force on the object. And that is the force of tension. That's what's moderating its acceleration from being 9.8 meters per second squared to being 4.13 meters per second squared.
Yeah.
So essentially, what is the net force on this object? On just this object. The net force is, and you can ignore what I said before about the net force, all the other pieces. But we know that the object, is accelerating downwards. Well, we know it's 20 kilograms. We know that it's accelerating downwards. 4.1. The net force, 20 times 20, is 82, let's say 83 newtons. 83 newtons down. We know that the net force is 83 newtons down. We also know that the tension force plus the force of gravity. What's the force of gravity? The force of gravity is just the weight of the object. So that the force of tension, which goes up, plus the weight of gravity, the force of gravity, is equal to the net force. And the way I set this up, tension is going to be a negative number, just because I'm saying positive numbers are downwards, so negative number will be upwards. So tension will be what is 83 divided by minus 196 is equal to minus 113 newtons. And the only reason why I got a negative number is because I used positive numbers for downwards. So minus 113 newtons downwards, which is the same thing as 113 newtons upwards. And so that is the tension in the rope. And you could have done the same thing on this side of the problem. What would have been? Well, yeah, you could have done the exact same thing on this side of the problem. You would have said, well, what would have accelerated naturally if there wasn't some force of tension on this rope going backwards? And you're saying, oh, well, we know it would have gone in this direction, some acceleration, but it's going the other direction. So you use that, figure out the net force, and you say the tension plus all of these forces have to equal the net force, and you should solve for the tension. And repeat the same thing. Now we will do a fun and somewhat simple, maybe instructive problem. So I have a pie. This is the pie. This is the pie. And I have my hand. You can tell that my destiny was really be a great artist. This is my hand, and I'm holding a pie, and I'm looking to smash this pie into this individual's face. Actually, wasn't. I was a newspaper cartoonist in high school, so I have some minor thing. Oh man, I should be focusing on drawing. I'm thinking, let's have a mustache. Anyway, I'm looking to throw this pie into this guy's face. And the problem is I need to figure out how fast do I need to accelerate this pie for it to not fall down, right? Because what's happening? Well, there's a force of gravity on this pie. There's a force of gravity on this pie. And if I don't accelerate it fast enough, it's just going to slide down. And I'll never be able to, it'll never reach the guy's face. So I don't want this pie to slide down at all. How far fast do I have to push it? Well, we know that the coefficient of friction, you don't know this, but I know that the coefficient of friction between my hand and the pie, the coefficient of friction is equal to 0.8. So given that, how fast do I have to accelerate? Let's see what's happening. So we have the force of gravity pulling down. So let's say that the mass of the pie is m. M equals mass. So what is the force of gravity pulling down on the pie? Well, the force of gravity is just equal to m times 9.8. Force of gravity is equal to m times 9.8. In order for this pie to not move down, what do we know about the net forces on that pie? Well, we know that the net forces on that pie have to be 0. So what would be the offsetting force? What would be the force of friction? So we would have a force of friction acting upwards, right? Because the force of friction always acts opposite of the direction that the thing would move otherwise. So essentially, our force of friction has to be greater than, roughly, greater than or equal to. Because if it's greater than, it's not like the pie is going to move up. Friction by itself will never move something. It'll just keep something from being moved. Let's just figure out the minimum. The force of friction has to be equal, similarly, to 9.8 times the mass of the pie. So if the coefficient of friction is 0.8, what is the force that I have to apply? Well, the force I have to apply in this case is going to be the normal force, right? That's normal to the bottom of the pie, right? I am like my hand is now like the surface of the ramp. So this is the normal force. And we know that the force of friction is equal to the coefficient of friction times the normal force. Let me switch colors. So, and the force of friction we know has to be 9.8 times the mass. So 9.8 meters per second times the mass. 9.8 m is the force of friction. And that has to equal the coefficient of friction times the normal force. Remember, the normal force is essentially the force that I'm pushing the pie with. We know this is 0.8, so we have 9.8 times the mass. It's not meters, that's the mass. Is equal to 0.8 times the normal force. And so we have normal force is equal to 9.8 times the mass divided by 0.8. It's 9.8 divided by 0.8. 9.8 divided by 0.8 is equal to 12.25. The normal force I have to apply is 12.25 times the mass. So that's the force I'm applying, times the mass. We don't know the mass of the pie. So how fast am I accelerating the pie? Well, force is equal to mass times acceleration. This is the force. 12.25 m, that's the force, is equal to the mass times the acceleration of the pie, right? It's the same pie that we're dealing with all the time, it's still m. You can take out m from both sides of the equation. So the acceleration, the rate at which I have to change the velocity, or the acceleration that I have to apply to the pie, is 12.25 meters per second squared. So actually, I have to apply more than 1 g, right? Because g is the force of gravity. And gravity accelerates something at 9.8 meters per second squared. So I have to do something at 12. I have to push and accelerate the pie at 12.25 meters per second squared. So something a little over 1 g in order for that pie to not fall, and in order for my normal force to provide a force of friction so that the pie can reach this bald man's face. I will see you in the next video. I mentioned in the last several videos that the coefficient of kinetic friction tends to be less. Sometimes it'll be roughly equal to the coefficient of static friction. But this might lead you to at least a question that I've had in my mind, and I still have to some degree, is why is the coefficient of kinetic friction lower, or why can it be lower? And the current best theory that I can visualize in my head, and based on reading that I've done, is the difference between. So let's think about it this way. So if we look at it at a kind of a regular human level, maybe we have a block. So this is the static case. So let's think about the static case over here. So I'll draw the static case over here. So I have a block that is stationary on top of the surface in a different color, on top of some type of surface right over here. And over here, I'm going to have a block moving at a constant velocity, relative to some surface, relative to the same surface. And so we draw it out. So this is moving at some constant velocity. constant velocity. And so the interesting thing here is, assuming these are the same masses, that these are the same surfaces, is why should the coefficient of friction here, why should the coefficient of static friction, so here, since this is stationary, what's under the coefficient of static friction, why should that be larger than the coefficient of kinetic friction over here? Why should that be larger than the coefficient of kinetic friction? Or another way to think about it is, you would need to apply more force to overcome the static friction here and start to get this accelerated. Then you would need to apply to get this already moving body to accelerate, because there would be kind of a less of a responsive friction force. So let's think about that a little bit. So what I'm going to do is zoom in into the atomic level. And so when you zoom into the atomic level, almost nothing is completely smooth. So this surface over here, might look something like this. So I'm going to draw the molecules that make up the surface. So the best to my ability. So the molecules, when you zoom up really close for the surface, might look something like this. And when we're really zooming into the atomic level, unimaginably small, but much smaller than that box I just drew. But I'm just trying to look at what's happening with the atoms where they contact, the molecules where they contact. And the box's molecules might look something like this. The box's molecules might look something like this. They aren't completely smooth. And hopefully this video also emphasizes that all of these forces and all this contact that we're talking about in these videos, and it's actually interesting philosophically, nothing is ever really in contact with each other. You really just have atoms that are repulsing each other because they're electrons. The electromagnetic force of repulsion between them is not allowing them to get any closer together. So that's all. When you push something, it's just the electrons in your hand pushing on the electron, or the electron clouds in your hand, pushing on the electron clouds of, say, the pen you're holding, or the key on your keyboard, or the mug, so that it repulses and causes it to go in the other direction. So that there's never any of this thing like real, what we imagine in our heads, real contact. And if you really want to blow your mind and watch the chemistry videos, if you want to understand this, is that most of these atoms are actually free space themselves. The electron cloud is huge relative, or I guess where most of the probability of finding the electron is huge compared to the size of the electron or the size of the nucleus. So it's kind of just a lot of free space pushing on a lot of other free space through the electromagnetic force. But anyway, we're talking about friction here. So if you were to really zoom in here, when this thing is stationary, you have the surfaces aren't actually even. And so you can imagine that these molecules that you have sometimes when it's sitting stationary, they might be kind of fit into each other. They've kind of slid into maybe these little ruts here and there. And so if you're trying to move this object, if you're trying to accelerate it to the left with some force, you have to overcome essentially either, for example, this part right over here either has to somehow break off, or the whole thing has to be shifted up a couple of atoms or a couple of molecules, or maybe this part over here has to be broken off or has to be shifted down one atom. You wouldn't notice these things. We wouldn't notice the shifting of a block or the shifting of the core. You wouldn't notice it by the width of a molecule or diameter of an atom or a molecule. But that's essentially what you're going to have to do, or you have to rip them off entirely in order to start this thing moving. Once something is already moving, and this is at least how I think about it, it doesn't have a chance to settle into these little ruts. So let me draw something that's already moving. I'll try to draw a similar surface. So I'm trying to draw the surface that looks essentially just like the one I drew. So maybe it looks like that. It's supposed to be the same surface. But once it's moving, it's kind of it's not sitting in these ruts anymore. The whole thing is moving, so it's kind of sliding across the top. And so now it might look something like this. I'll try my best to draw it. So now it might look something like this. Maybe this has been shifted up a little bit so that it can start sliding, and you've overcome overcame the static friction. So now it is. Let me draw the same. Trying to draw the same surface here, so give or take. So now it's moving. It doesn't have a chance to really settle in. It has to kind of bounce along top. And so that's the best understanding. And so the real force of the friction here, there will be still some, as it's moving along, it still might every now and then bounce into little ruts here and there. But you also have any type of chemical bonds that form between the atoms temporarily that keep breaking and forming. And in order to keep this thing, I guess, moving, or especially if you want to accelerate it, you're going to have to keep breaking these bonds. So that's essentially the force of friction that you're overcoming. Here, you might have those same bonds, and not only do you have those same bonds, you also have to overcome these ruts, or these little ragged parts that have time to settle into these little nooks that you have to overcome even more. So that's the intuition. This is actually still an area of research. So it's not like this cut and dry thing. It's a fun thing to think about what's happening at the atomic level. But this is the general intuition why the coefficient of static friction is higher than the coefficient of kinetic friction. So I've got this block of wood here that has a mass of 5 kilograms, and it's sitting on some dirt. And we're near the surface of the Earth. And the coefficient of static friction between this type of wood and this type of dirt is 0.60. And the coefficient of kinetic friction between this type of wood and this type of dirt is 0.55. This was measured by someone else long ago, or you found it in some type of a book someplace. And let's say we push on this side of the block with a force of 100 newtons. What is going to happen? So the first thing you might realize is if there was no friction, if this was a completely frictionless boundary and there's no air resistance, we are assuming that there is no air resistance in this example, that in this dimension, in the horizontal dimension, there would only be one force here. There would be 100 Newton force. It would be completely unbalanced. And that would be the net force. And so you would have a force going in that direction of 100 Newtons on a mass of 5 kilograms. Force is equal to mass times acceleration. Acceleration and force are vector quantities. And so you would have the force divided by the mass would give you 20 meters per second of acceleration in the right direction. That's if there were no friction. But there is friction in this situation. So let's think about how we'll deal with it. So the coefficient of friction tells us, so this right here is the ratio between the magnitude of the force that I call the budging force, the amount of force you need to apply just to get this thing to budge, just to get this thing to start moving, so we can start using the coefficient of kinetic friction. It's the ratio between that and the magnitude of the force of contact between this block and the floor or the ground here. And the magnitude of that force of contact is the same thing as the normal force that the ground is applying on the block. The magnitude of the normal force that the ground is applying on the block. Then once it's moving, then we can say that this is going to be, that this will then be equal to, this over here will be equal to the force of friction. So this is the force necessary to overcome friction, and then this over here will be equal to the force of friction, the magnitude of the force of friction over the force of contact, the contact force between those two, so over the normal force. And it makes sense that the larger the contact force, the more that these are being pressed together, the little at the atomic level, they kind of really get into each other's grooves, the more budging force you would need, or the more friction force would go against your motion. And in either situation, the force of friction is going against your motion. So even if you push it on that way, it's not like force of friction is all of a sudden going to help you. So let's think about what the necessary force we need to do to overcome the force of friction right here in the static situation. So the force of gravity on this block, is going to be the gravitational field, which is 9.8 meters per second, times 5 kilograms. 9.8 meters per second times 5 kilograms gives us 49 kilogram meters per second, or 49 newtons down. This is the force, the magnitude of the force due to gravity. The direction is straight down towards the center of the Earth. The normal force, and that force is there because this block is not accelerating downwards. So there must be some force that completely balances off the force of gravity. And in this example, it is a normal force. It is the normal force. So it is acting 49 newtons upward. And so these net out, and that's why this block does not accelerate upwards or downwards. So what we have is the magnitude of the budging force needs to be equal over the magnitude of the normal force. Well, this thing right over here is going to be 49 newtons, is equal to 0.60. Or we could say that the magnitude of the budging force is going to be equal to 49 newtons times the coefficient of static friction, or that's 49 newtons times 0.60. 0.60. And remember, coefficients of friction are unitless, so the units here are still going to be in newtons. And so this gives us, get out our calculator, this gives us 49 times 0.6 gives us 29.4 newtons. This is equal to, we write it, 29.4 newtons, 29.4 newtons. So that's the force necessary to overcome static friction, which we are applying more than enough of. So with 100 newtons, we will just start to budget. And right when we're just at that moment where the thing is just starting to move, the net force, so we have 100 newtons going in that direction, and the force of static friction is going to go in this direction. Maybe I can draw it down here, so it's coming from right over here. The force of static friction is going to be 29.4 newtons that way. And so right when I'm just starting to budge this, just for that little, moment, it's not because once I do that, then all of a sudden it's moving, and then kinetic friction starts to matter. But just for that moment, I'll have a net force of 100 minus 29.4 to the right. So I'll have a net force of 70.6. So I will have a net force of 70, what did I just write there? 70.6, I can do that in my head, I should just look at that. 70.6 newtons for just a moment while I budget. So just exactly while I'm budgeting it, while we're overcoming the static friction, we have a 70.6 Newton net force in the right direction. And so just for that moment, we divide it by 5 kilogram mass. 5 kilogram mass. So just for that moment, it'll be accelerating at 14.12 meters per second. So you'll have an acceleration of 14.1 meters per second squared to the right. But that will just be for that absolute moment, because once I budget, all of a sudden the block will start to be moving. And once it's moving, the coefficient of kinetic friction starts to matter. We got things out of their little grooves, and so they're kind of gliding past each other on the top, although there still is resistance. So once we budget, we'll have the acceleration for just a moment. Now all of a sudden the coefficient of kinetic friction comes to play. And the force of friction, assuming we're moving, the magnitude of the force of friction, it'll always go against our movement, is going to be, remember our normal force, we already said is 49 newtons. So it's 49, we multiply both sides of this times 49. You get 49 newtons times 0.55, which is equal to 49 times 0.55 is equal to 26.95 newtons. So it's equal to 26.95 newtons. This is the force of friction. This is the magnitude, and it's going to go against our motion. So as soon as we start to move in that direction, the force of friction is going to be going in that direction. So once we start moving, assuming that I'm continuing to apply this 100 newtons of force, what is the net force? So I have 100 newtons going that way, and I have 26.95 newtons going that way. 26.95. And remember, vectors, I don't have to draw them here. I can draw all of them, so all of their tails start at the center of mass of this object. I can draw them whenever, but remember, this is acting on the object. So it's usually, if you want to be precise, you show it acting on the center of mass. So we can do all of these atoms as one collective object. But anyway, what is the net force now? Well, you have 100 newtons to the right, you have 26.95 newtons to the left, 100 minus 26.95, 100 newtons that I'm applying to the right, minus 26.95 newtons, which is the force of friction to the left, always acting against us, means that there's a net force to the right of 73.05.
So once we're moving, we have a net force to the right of 73.05 newtons. This is the net force. This is the net force, and it's acting to the right. So what is going to be, once right after we budget, how quickly will this accelerate? Well, 73.05 divided by the mass, divided by 5 kilograms, divided by 5 kilograms, gives us 14.61. So the acceleration once we're moving is going to be 14.61 meters per second squared to the right, to the right. So I really want to make sure you understand what's happening here. It took us, we always had enough force to start budging it. But right when we budgeted, that we kind of had to overcome the static friction. For a moment, our acceleration was slower. Our acceleration was slower because we're overcoming that static friction. But once we've budgeted, and once it's moving, and assuming that we're continuing to apply a constant force over here, then all of a sudden the force of friction, since we're kind of bumping along the top now, and it's not stuck in their grooves, we're now using the coefficient of kinetic friction. And so once it's moving, the net force becomes greater in the rightward direction, because you can kind of view it as the force of friction will become less once it starts moving. And so now the force of friction went down a little bit to 26.95 newtons. And so now we are accelerating to the right a little bit at a slightly faster rate, 14.61 meters per second. So right when you budget, accelerate at 14.1 meters per second, but just for a moment, almost an unnoticeable moment, once it starts moving, then you're going to be going to the right with this constant acceleration.
Welcome back. I'm now going to introduce you to the concepts of work and energy. And these are two words that I'm sure you use in your everyday life already, and you have some notion of what they mean, but maybe just not in the physics context, although they're not completely unrelated. So work, you know what work is. Work is when you do something. You go to work, you make a living. In physics, work is, and I'm going to use a lot of words, and they actually end up being kind of circular in their definitions. But I think when we start doing the math, we'll start to get at least a slightly more intuitive notion of what they all are. So work is energy transferred by a force. So I'll write that down. Energy transferred. And I got this from Wikipedia because I wanted a good, I guess, relatively intuitive definition. Energy transferred by a force. And that makes reasonable sense to me. But then you're wondering, well, I know what a force is. You know, force is mass times acceleration. But what is energy? And then I looked up energy in Wikipedia. And I found this, well, entertaining, but it also, I think, tells you something, that these are just concepts that we use to, I guess, work with what we perceive as motion and force and work and all of these types of things. But they really aren't independent notions. They're related. So Wikipedia defines energy as the ability to do work. So they kind of use each other to define each other, ability to do work, which is frankly as good of a definition as I could find. And so with just the words, these kind of don't give you much information. So what I'm going to do is move on to the equations, and this will give you a more quantitative feel of what these words mean. So the definition of work in mechanics: work is equal to force times distance. So let's say that I have a block, and I'm going to do it in a different color just because this yellow might be getting tedious. And I apply a force of, let's say I apply a force of 10 newtons, and I move that block by applying a force of 10 newtons. I move that block, let's say I move it, I don't know, 7 meters. 7 meters. So the work that I apply to that block, or the energy that I transferred to that block, the work is equal to the force, which is 10 newtons, times the distance, times 7 meters. That would equal 70, 10 times 7, Newton meters. So Newton meters is one I guess, way of describing work. And this is also defined as 1 joule. And I'll do another presentation on all the things that joule did. But joule is the unit of work, and it's also the unit of energy. And they're kind of transferable, because as we look at the definitions that Wikipedia gave us, work is energy transferred by a force, and energy is the ability to do work. So I'll leave this relatively circular definition alone now. But we'll use this definition, which I think helps us a little bit more, to understand the types of work we can do, and then what kind of energy we actually are transferring to an object when we do that type of work. So let me do some examples. let's say I have a block. I have a block of mass m. I have a block of mass m, and it starts at rest. And then I apply force. Let's say I apply a force F for a distance. For a distance of, I think you can guess what the distance I'm going to apply it is. For a distance of d. So I'm pushing on this block with a force of F for a distance of d. And what I want to figure out is, well, we know what the work is, by definition. Whoops. Work is equal to this force times this distance that I'm applying block, that I'm pushing the block. But what is the velocity going to be of this block over here, right? It's going to be something somewhat faster, right? Because force isn't, and I'm assuming that this is frictionless on here. So force isn't just moving the block with a constant velocity. Force is equal to mass times acceleration. So I'm actually going to be accelerating the block. So even though it's stationary here, by the time we get to this point over here, that block is going to have some velocity. We don't know what it is because we're using all variables, we're not using numbers. But let's figure out what it is in terms of v. So if you remember your kinematics equations, and if you don't, you might want to go back, or if you've never seen the videos, there's a whole set of videos on projectile motion and kinematics. But we figured out that when we're accelerating an object over a distance, that the final velocity, change colors just for variety, the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times the distance. And we proved this back then, so I won't redo it now. But in this situation, what's the initial velocity? Well, the initial velocity was 0, right? So the equation becomes vf squared is equal to 2 times the acceleration times the distance. And then we could rewrite the acceleration in terms of the force and the mass, right? So what is the acceleration? F equals ma, or acceleration is equal to force divided by mass. So we get vf squared is equal to 2 times the force divided by the mass times the distance. And then we can take the square root of both sides if we want. We get the final velocity of this block at this point is going to be equal to the square root of 2 times force times distance divided by mass. And so that's how we could figure it out. And there's something interesting going on here. There's something interesting in this, what we did just now. Do you see something that looks a little bit like work? Well, sure. You have this force times distance expression right here. Force times distance right here. So let's write another equation. If we know the given amount of velocity something has, if we can figure out how much work needed to be put into the system to get to that velocity, well, we can just replace force times distance with work. Force times distance. So let's go straight from this equation because we don't have to re-square it. So we get vf squared is equal to 2 times force times distance. That's work. That definition right here. 2 times work divided by the mass. Let's multiply both sides of this equation times the mass. So you get mass times the velocity. And we don't have to write, I'm going to get rid of this f because we know we started at rest and the velocity is going to be, let's just call it v. So m times v squared is equal to 2 times the work. Let's divide both sides by 2, or that the work is equal to m v squared over 2. Just divide both sides by 2. And of course, the unit here is joules. So this is interesting. Now, if I know the velocity of an object, I can figure out, using this formula, which hopefully wasn't too complicated to derive, I can figure out how much work was imputed into that object to get it to that velocity. And this, by definition, is called kinetic energy. This is kinetic energy. And once again, the definition that Wikipedia gives us is the energy due to motion, or the work needed to accelerate from an object from being stationary to its current velocity. And I'm actually almost out of time, but what I will do is I will leave you with this formula, that kinetic energy is mass times velocity squared divided by 2, or 1/2 mv squared. It's a very common formula. And I'll leave you that, and that is one form of energy. And I'll leave you with that idea. And in the next video, I will show you another form of energy. And then I will introduce you to the law of conservation of energy. And that's where things become useful, because you can see how one form of energy can be converted to another to figure out what happens to another. I'll see you soon. Welcome back. In the last video, I showed you, or hopefully I did show you, that if I apply a force of F to an initially stationary object with mass m, and I apply that force for a distance d, that force times distance, the force times the distance that I'm pushing the object, is equal to 1/2 mv squared, where m is the mass of the object, and v is the velocity of the object after pushing it for a distance of d. And we defined in that last video, we just said that this is work. Force times distance, by definition, is work. And 1/2 mv squared, I said this is called kinetic energy. Kinetic energy. And so by definition, kinetic energy is the amount of work, and I mean, this is the definition right here. It's the amount of work you need to put into an object or apply to an object to get it from rest to its current velocity. So its velocity over here. So let's just say I looked at an object here with mass m and it was moving with velocity v. I would say, well, this has a kinetic energy of 1/2 mv squared. If the numbers are confusing you, let's say the mass was, I don't know, let's say this was a 5 kilogram object and it's moving at 7 meters with mass m and it was moving with the velocity v. I would say, well, this has a kinetic energy of 1/2 mv squared. If the numbers are confusing you, let's say the mass was, I don't know, let's say this was a 5 kilogram object and it's moving at 7 meters per second. So I would say the kinetic energy of this object is going to be 1/2 times the mass times 5 times 7 squared times velocity squared times 49. So let's see, 1/2 times 49, that's a little under 25. So it'll be approximately 125 Newton meters, which is approximately 5, moving at 7 meters per second. So I would say the kinetic energy of this object is going to be 1/2 times the mass times 5 times 7 squared times velocity squared times 49. So let's see, 1/2 times 49, that's a little under 25. So it'll be approximately 125 Newton meters, which is approximately, and the Newton meter is just a joule, 125 joules. So this is if we actually put numbers in. And so when we immediately know this, even if we didn't know what happened, how did this object get to this speed? Let's say we didn't know that someone else had applied a force of m for a distance of d to this object. Just by calculating its kinetic energy as 125 joules, we immediately know that that's the amount of work that was necessary. And we don't know if this is exactly how this object got to this velocity, but we know that that is the amount of work that was necessary to accelerate the object to this velocity of 7 meters. Work that was necessary to, and we don't know if this is exactly how this object got to this velocity, but we know that that is the amount of work that was necessary to accelerate the object to this velocity of 7 meters per second. So let's give another example. And instead of this time just pushing something in a horizontal direction and accelerating it, I'm going to show you an example. We're going to push something up, but its velocity really isn't going to change. Let's say I have a different situation, and we're on this planet, we're not in deep space. I have a mass of m, and I were to apply a force. Let's say the force that I applied is equal to mass times the acceleration of gravity. Mass times, let's just call that gravity, right? 9.8 meters per second squared. And I were to apply this force for a distance of d upwards, right? Or instead of d, let's say h for height, right? So in this case, the force times the distance is equal to, the force is mass times the acceleration of gravity, right? And remember, I'm pushing with the acceleration of gravity upwards, while the acceleration of gravity is pulling downwards. So let's say, so the force is mass times gravity, and I'm applying that for a distance of h, right? B is h, so the force is this. This is the force. And then the distance I'm applying is going to be h. And what's interesting is, and this is a bit of, I mean, if you want to think of an exact situation, imagine an elevator that is already moving, because you would actually have to apply a force slightly larger than the acceleration of gravity just to get the object moving. But let's say that the object is already at constant velocity. Let's say it's an elevator. And it is just going up with a constant velocity. And let's say the mass of the elevator is, I don't know, 10 kilograms. 10 kilograms. And it moves up with a constant velocity. It moves up, I don't know, it moves up 100 meters. So we know that the work done by whatever was pulling on this elevator, probably was the tension in this wire that was pulling up on the elevator. But we know that the work done is the force necessary to pull up on it. Well, that's just going to be the force of gravity. So we're assuming that the elevator is not accelerating, right? Because if the elevator was accelerating upwards, then the force applied to it would be more than the force of gravity. And if the elevator was accelerating downwards, or if it was slowing down upwards, then the force being applied would be less than the acceleration of gravity. But since the elevator is at a constant velocity moving up, we know that the force pulling upwards is completely equal to the force pulling downwards, right? No net force, because gravity and this force are at the same level, so there's no change in velocity. I said that 2 times. So we know that this upward force is equal to the force of gravity. So this is, at least in magnitude, in the opposite direction. So this is mg. So what's m? M is 10 kilograms times the acceleration of gravity. Let's say that's 9.8 meters per second squared. I'm not writing the units here, but we're all assuming kilograms or meters per second squared. We're moving that for a distance of 100 meters. 100 meters. So how much work was put into this elevator, I guess, or into this object, it doesn't have to be an elevator, by whatever force that was essentially pushing up on it or pulling up on it. And so this would be 98 times 100. So it's 9,800 Newton meters or 9,800 joules. And when we're at the top of, after we've moved up 100 meters, notice there's no change in velocity. So the question is, where did all that work get put into the object? And the answer here is that the work got transferred to something called potential energy. So, and potential energy is defined as, well, gravitational potential energy. We'll work with other types of potential energy later with springs and things. Potential energy is defined as mass times force of gravity times the height that the object is at. And why is this called potential energy? Because at this point, the energy work had to be put into the object to get it to this, in the case of gravitational potential energy, work had to be put into the object to get it to this height. But the object now, it's not moving or anything, so it doesn't have any kinetic energy, but it now has a lot of potential to do work. What do I mean that? What do I mean by potential to do work? Well, after I move an object up 100 meters into the air, what's its potential to do work? Well, I could just let go of it and have no outside force other than gravity. The gravity will still be there. And because of gravity, the object will come down and be at a very, very fast velocity when it lands. And maybe I could apply this to some machine or something, and this thing could do work. And if that's a little confusing, let me give you an example. It all works together with our. So let's say I have an object that is, well, I don't know, a 1 kilogram object. We're on Earth, and let's say that it is 10 meters above the ground. 10 meters above the ground. So we know that its potential energy is equal to mass times gravitational acceleration times height. So mass is 1, gravitational acceleration, let's just say gravitational acceleration is 10 meters per second squared, times 10 meters per second squared, times 10 meters, which is the height. So it's approximately equal to 100 Newton meters, which is the same thing as 100 joules. Fair enough. And what did we know about this? We know that it would take about 100, or exactly 100 joules of work to get this object from the ground to this point up here. Now, what we can do now is use our traditional kinematics formulas to figure out, well, if I just let this object go, how fast will it be when it hits the ground? And we can do that, but what I'll show you is even a faster way. And this is where all of the work and energy really becomes useful. We have something called the law of conservation of energy, is that energy cannot be created or destroyed. It just gets transferred from one form to another. And there's some minor caveats to that, but for our purposes, we'll just stick with that. So in the situation where I just take the object and I let go up here it has a ton of potential energy, right? And by the time it's down here, it has no potential energy because the height becomes 0, right? What's its potential energy? So here, potential energy is equal to 100. And here, potential energy is equal to 0. And so the natural question is, I just told you the law of conservation of energy, but if you look at this example, all the potential energy just disappeared. And it looks like I'm running out of time, but what I'll show you in the next video is that potential energy gets converted into another type of energy. I think you might be able to guess what type that is because this object is going to be moving really fast right before it hits the ground. I'll see you in the next video.
In order to transfer energy to an object, you've got to exert a force on that object. The amount of energy In order to transfer energy to an object, you've got to exert a force on that object.
Oh. Punch the teddy bear. I have to use the restroom.
Yeah.
The amount of energy transferred by a force. In order to transfer energy to an object, you've got to exert a force on that object. The amount of energy transferred by a force is called the work done by that. Force. The formula to find the work done by a particular force on an object is W equals FD cosine theta. W refers to the work done by the force F. In other words, sine theta. W refers to the work done by the force F. In other words, W is telling you the amount of energy that the force F is giving to the object. F refers to the size of the particular force doing the work. D is the displacement of the object, how far it moved while the force was exerted on it. And the theta in cosine theta refers to the angle between the force doing the work and the displacement of the object. You might be wondering, what this cosine theta is doing in here. This cosine theta is in this formula because the only part of the force that does work is the component that lies along the direction of the displacement. The component of the force that lies perpendicular to the direction of motion doesn't actually do any work. We know perpendicular to the direction of motion doesn't actually do any work. We notice a few things about this formula. The units for work are newtons times meters, which we call joules. Joules are the same unit that we measure energy in, which makes sense because work is telling you the amount of joules given to or taken away from an object or a system. If the value of the work done comes out to be positive for a particular force, it means that that force is trying to give the object energy. The work done by a force will be positive if that force or a component of that force points in the same direction as the displacement. And or a component of that force done by a force will be positive if that force or a component of that force points in the same direction as the displacement. And if the value of the work done comes out to be negative, it means that that force is trying to take away energy from the object. The work done by a force will be negative if that force or a component of that force points in the opposite direction as the displacement. If a force points in a direction that's perpendicular to the displacement, the work done by that force is zero, which means it's neither giving displacement. The work done by that force is zero. which means it's neither giving nor taking away energy from that object. Another way that the work done by a force could be zero is if the object doesn't move, since the displacement would be zero. So the force you exert by holding a very heavy weight above your head does not do any work on the weight, since the weight is not moving. So this formula represents the definition of the work done by a particular force. But what if we wanted to know the net work or total work done on an object? We could just find the individual amounts of work done by each particular force and add them up. But there's actually a trick to figuring out the net work done on an object. To keep things simple, let's assume that all the forces already lie along the direction of the displacement. That way we can get rid of the cosine theta term. Since we're talking about the net work done on an object, I'm going to replace F with the net force on that object. Now, we know that the net force is always equal to the mass times the acceleration. So we can replace F net with m times a. So we find that the net work is equal to the mass times the acceleration times the displacement. I want to write this equation in terms of the velocities and not the acceleration times the displacement. So I'm going to ask that you recall a 1D kinematics equation that looked like this. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. In order to use this kinematic formula, we've got to assume that the acceleration is constant, which means we're assuming that the net force on this object is constant. Even though it seems like we're making a lot of assumptions here, getting rid of the cosine theta and assuming the forces are constant, none of those assumptions are actually required to derive the result we're going to attain. They just make this derivation a lot simpler. So looking at this kinematic formula, we see that it also has acceleration times displacement. So I'm just going to isolate the acceleration times the displacement on one side of the equation, and I get that A times D equals V final squared minus V initial squared divided by 2. Since this is what A times D equals, I can replace the A times D in my net work formula, and I find that the net work is equal to the mass times the quantity V final squared minus V initial squared divided by 2. If I multiply the terms in this expression, I get that the net work is equal to 1/2 mass times the final velocity squared minus 1/2 mass times the initial velocity squared. In other words, the net work or total work is equal to the difference between the final and initial values of 1/2 mv squared. This quantity 1/2 m times v squared is what we call the kinetic energy of the object. So you'll often hear that the net work done on an object is equal to the change in the kinetic energy of that object. And this expression is often called the work energy principle. Since it relates the net work done on an object to the kinetic energy gained or lost by that object. If the net work done is positive, the kinetic energy is going to increase and the object's going to speed up. If the net work done on an object is negative, the kinetic energy of that object is going to decrease, which means it's going to slow down. And if the net work is going to speed up. If the net work done on an object is negative, the kinetic energy of that object is going to decrease, which means it's going to slow down. And if the net work done on an object is 0, it means the kinetic energy of that object is going to stay the same, which means the object maintains a constant speed. Negative, gained, or called the work energy principle, since it relates the net work done on an object to the kinetic energy gained or lost by that object. If the net work done is positive, the kinetic energy is going to increase and the object's going to speed up. If the net work done on an object is
Power. Power.
negative, object. One way to find the amount of work done
Babe, the food's ready.
Huh?
The food's ready.
Food?
Yeah, you hungry?
Yeah.
Oh, okay. Well, listen, I'm probably just gonna eat and keep watching
They
videos.
even make food?
Yeah,
Well, nice of it.
right? That's what I thought.
Yeah.
Alright, let's get some food.
Doing it without me.
Right?
Nice. Good job. Can you pass me the charger, please? Thank you. So is that okay? Make sure your brother Ted is okay.
Mm-hmm.
cosine theta. But this number for
Okay,
the
yeah.
amount of work done represents the amount of energy transferred to an object. For instance, if you solve for the work done and you get positive 200 joules, it means that the force gave something 200 joules of energy. So if you have a way of determining the amount of energy that something gains or loses, then you have an alternate way of finding the work done, since the work done on an object is the amount of energy it gains or loses. For instance, imagine a 50-kilogram skateboarder that starts at rest. If a force starts the skateboarder moving at 10 meters per second, that force did work on the skateboarder since it gave the skateboarder energy. The amount of kinetic energy gained by the skateboarder is 2,500 joules. That means that the work done by the force on the skateboarder was positive 2,500 joules. It's positive because the force on the skateboarder gave the skateboarder 2,500 joules. If a force gives energy to an object, then the force is doing
Oh, he's finally there.
It
Oh,
is.
no, he's gone. Okay.
positive work on that object. And if a force takes away energy from an object, the force is doing negative work on that object. Now imagine that the skateboarder who's moving with 10 meters per second gets stopped because he crashes into a stack of bricks. The stack of bricks does negative work on the skateboarder because it takes away energy from the skateboarder. To find the work done by the stack of bricks, we just need to figure out how much energy it took away from the skateboarder. Since the skateboarder started with 2,500 joules of kinetic energy and ends with 0 joules of kinetic energy, it means that the work done by the bricks on the skateboarder was negative 2,500 joules. It's negative because the bricks took away energy from the skateboarder. Let's say we instead lift the bricks, which are 500 kilograms, upwards a distance of 4 meters. To find the work that we've done on the bricks, we could use FD cosine theta, but we don't have to. We could just figure out the amount of energy that we've given to the bricks. The bricks gain energy here, and they're gaining gravitational potential energy, which is given by the formula mgh. If we solve, we get that the bricks gain 19,600 joules of gravitational potential energy. That means that the work we did on the bricks was positive 19,600 joules. It's positive because our force gave the bricks energy. This idea doesn't just work with gravitational potential energy and kinetic energy, it works for every kind of energy. It's M, you just figure out energy from the skateboarder. Let's say we instead lift the bricks, which are 500 kilograms, upwards a distance of 4 meters. To find the work that we've done on the bricks, we could use FD cosine theta, but we don't have to. We could just figure out the amount of energy that we've given to the bricks. The bricks gain energy here, and they're gaining gravitational potential energy, which is given by the formula mgh. If we solve, we get that the bricks gain 19,600 joules of gravitational potential energy. That means that the work we did on the bricks was positive 19,600 joules. It's positive because our force gave the bricks energy. This idea doesn't just work with gravitational potential energy and kinetic energy, it works for every kind of energy. You can always find the work done by a force on an object if you can determine the energy that that force gives or takes away from that object. I'm going to show you some examples of how to solve problems involving work. Imagine a 4-kilogram trash can. The trash can is disgusting, so someone ties a string to it and pulls on the string with a force of 50 newtons. The force of kinetic friction on the trash can while it slides is 30 newtons. The trash can slides across the ground for a distance of 10 meters. Let's try to find the work done by each force on the trash can as it slides across the ground. To find the work done by each force, we should recall the formula definition of work. Work equals FD cosine theta, where theta is the angle between the force doing the work and the direction the trash can is moving. There are 4 forces involved here: tension, the normal force, the gravitational force, and the force of kinetic friction. In finding the work done for all of these forces, the displacement is going to be 10 meters, but the value of the force and the angle between that force and the displacement is going to differ for each of the forces. For instance, to find the work done by the force of tension, we'll plug in the size of the tension, which is 50 newtons, the displacement is 10 meters, and since the tension force is pointed in the same direction as the displacement, the angle between the force of tension and the displacement is 0 degrees. And since cosine of 0 is 1, the work done by the tension force is 500 joules. To find the work done by friction, we'll plug in the size of the force of friction, which is 30 newtons. The displacement is still 10 meters, and since the force of friction points in the opposite direction as the displacement, the angle between the force of friction and the displacement is 180 degrees. Since cosine of 180 is -1, the work done by the force of friction is -300 joules. Now let's figure out the work done by the gravitational force. The force of gravity is mg, so the force of gravity is 4 kilograms times 9.8 meters per second squared, which is 39.2 newtons. The displacement is again 10 meters. But the angle between the gravitational force and the direction of the displacement is 90 degrees in this case. And since cosine of 90 is 0, the gravitational force does no work on this trash can. Similarly, if we were to find the work done by the normal force, the angle between the direction of the displacement and the normal force is 90 degrees, so the normal force also does no work on the trash can. This makes sense because forces that are perpendicular to the motion can never do any work on that object. So that's how you can find the work done by individual forces. And if we wanted to know the net work done on this trash can, we could just add up the work done by each individual force. So the net work is going to be 200 joules. Now that we know the net work done on the trash can, we can use the work energy principle to figure out the speed of the trash can after it slid the 10 meters. The work energy principle says that the net work done on an object is equal to the change in kinetic energy of that object. So 200 joules is going to equal the difference in kinetic energy. If we assume the trash can started at rest, which seems reasonable, the initial velocity is 0. So we can solve for the final speed of the trash can, which comes out to be 10 meters per second. This time, let's say you take the trash can and lift it upwards with a constant velocity for a distance of 2 meters. In order to lift the trash can up with a constant velocity, you need to push with a force equal to the weight of the trash can, which means you have to push upwards with a force of 39.2 newtons. So to find the work done by the force that you exert, the force is going to be 39.2 newtons, the displacement is going to be 2 meters, and the angle between the force and the displacement is going to be 0 degrees because the direction of the force that you exert is in the same direction as the displacement of the trash can. So the work that you've done in lifting up this 4 kilogram trash can is 78.4 joules. To find the work done by the force of gravity, we can use the force of gravity, which is again 39.2 newtons. The displacement is again 2 meters, but the angle between the direction of the displacement and the gravitational force is 180 degrees because the displacement points up and the gravitational force points down. So the work done by the gravitational force is negative 78.4 joules, which means the net work done on the trash can is 0. And that makes sense because since the trash can moved upwards with constant velocity, there was no change in the kinetic energy of this object.
Thank you, Brett. Those are good today. Well, Yeah. Okay, we're back.
Nah.
You know why I like this? I want to frame this picture in my room.
Why?
I don't know. It keeps me motivated.
Motivated?
Yeah, I just picture this guy.
Yeah.
Because look, if you look at outside, he's
water.
water. So
Ocean.
I just picture him locked in a room, in some place he can't escape.
Huh?
And he's told to study for all eternity. Well, and he's
That's a horror story.
Well,
babe.
maybe he's just.
That's a horror story.
Why? Why is that a horror story? I feel like that's really cool.
That's called prison.
It's called what?
Prison.
Is that a me?
Prison.
Prison?
Alcatraz. That's literally Alcatraz. Right?
Wow.
Middle of the island. You're locked up. Study.
I don't know. To me, it sounds pretty cool.
How? You want to do that?
No, I mean, I
want to do it voluntarily, but I don't want to be locked up in the room and study whole day.
Yeah, but look, he's got weights. He's got his bed.
I don't think it's an island, baby. It's just like he's living near the ocean.
No, it's an island, though. It's an island. He's locked in there, and he's told to study. And if you study long enough, and you read everything, you understand everything, you can escape.
You can escape?
You can escape. You can escape.
Escape?
Yeah.
That's prison, babe. That's literally prison. Right?
He's planning his escape. But first he has to study.
Your way of prison.
It's called life.
That's called
The prison of life.
That's true.
Life is a prison.
Ha ha ha.
True. Okay, let's get back. All right. Up to you, Spencer. Oh.
Welcome back. At the end of the last video, I left you with a bit of a question. We had a situation where we had a 1 kilogram object. This is the 1 kilogram object, which I drawn here in this video. This is 1 kilogram. And we're on Earth, and it is, and I need to mention it because gravity is different from planet to planet. But as I mentioned, I'm holding it, let's say I'm holding it 10 meters above the ground. This distance, or this height, is 10 meters. 10 meters, and we're assuming the acceleration of gravity. Acceleration of gravity, if you also write it's just g, is, let's assume it's just 10 meters per second squared, just for the simplicity of the math, instead of the 9.8. So what we learned in the last video is that the potential energy in this situation, the potential energy, which equals m times g times h, is equal to the mass is 1 kilogram times the acceleration of gravity, so it's 10 meters per second squared. I'm not going to write the units down just to save space. You should do this when you do it on your test. And then the height is 10 meters. And the units, if you work them all out, it's meters or joules, and this equals, so
You can't even see.
joules. That's the potential energy when I'm holding it there. And I asked you, well, when I let go, what happens? Well, the block obviously will start falling, and not only falling, it will start accelerating to the ground at 10 meters per second squared, roughly. And right before it hits the ground, let me draw that in brown for ground. Right before the object hits the ground, or actually right when it hits the ground, what will be the potential energy of the object? Well, it has no height, right? Potential energy is mgh. The mass and the acceleration of gravity is the same, but the height is 0, so they're all multiplied by each other. So down here, the potential energy is going to be equal to 0. And I told you in the last video that we have the law of conservation of energy, that energy is conserved. It cannot be created or destroyed. It can just be converted from one form to another. But I'm just showing you, this object had 100 joules of energy, in this case, gravitational potential energy. And down here, it has no energy, or at least it has no gravitational potential energy. That's the key. That gravitational potential energy was converted into something else. And that something else it was converted into is kinetic energy. And in this case, since it has no potential energy, all of that previous potential energy, all of this 100 joules that it has up here, all of this 100 joules is now going to be converted to kinetic energy. And we can use that information to figure out its velocity right before it hits the ground. So how do we do that? Well, what's the formula for kinetic energy? And we solved it 2 videos ago, and hopefully it shouldn't be too much of a mystery to you. It's something good to memorize, but it's also good to know how we got it. Go back 2 videos that you forgot. So kinetic energy, so first, we know that all the potential energy was converted into kinetic energy. We had 100 joules of potential energy, so we're still going to have 100 joules, but now all of it's going to be kinetic energy. And kinetic energy is 1/2 mv squared. So we know that 1/2 mv squared, or the kinetic energy, is now going to equal 100 joules. What's the mass? The mass is 1. And we can solve for v now. 1/2 v squared equal 100 joules. V squared is equal to 200. And then we get v is equal to square root of 200, which is going to be 14.1 meters per second squared.
downwards, right before the object touches the ground, right before it touches the ground. And you might say, well, Sal, that's nice and everything. That's, we learned a little bit about energy, but what, I could have solved that, or hopefully you could have solved that problem just using your kinematics formula. So what's the whole point of introducing these concepts of energy? And I will now show you. So let's say they have the same 1 kilogram object up here, and it's 10 meters in the air, but I'm going to change things a little bit. I'm going to change things a little bit. So let me see if I can competently erase all of this. Nope, that's not what I wanted to do. Okay, there you go. Trying my best to erase this. All of this stuff. Okay. So I have the same object. It's still 10 meters in the air, and I'll write that in a second. And I'm still going to, and I'm just holding there, and I'm still going to drop it, but something interesting is going to happen. Instead of it going straight down, it's actually going to drop on this ramp of ice. So it's going to, ice has lumps on it, and it's kind of, and then this is the bottom. This is the ground down here. This is the ground. So what's going to happen this time? I'm still 10 meters in the air, so let me draw that. That's still 10 meters. Switch colors, just not everything is ice. So that's still 10 meters, but instead of the object going straight down now, it's going to go down here and then start sliding, right? It's going to go sliding along this hill, and then at this point, it's going to be going really fast in the horizontal direction. Right now, we don't know how fast. And just using our kinematics formula, this would have been a really tough formula. This would have been difficult. I mean, you would have had to, you could have attempted it, and it would actually have taken calculus because the angle of the slope changes continuously. We don't even know the formula for the angle of the slope. You would have had to break it out into vectors. You'd have to do all sorts of complicated things. This would have been a nearly impossible problem. But using energy, we can actually figure out what the velocity of this object is at this point. And we use the same idea. Here we have 100 joules of potential energy. We just figured that out. Down here, what's the height above the ground? Well, the height is 0. So all the potential energy has disappeared. And just like in the previous situation, all of the potential energy is now converted into kinetic energy. And so what is that kinetic energy going to equal? It's going to be equal to the initial potential energy. So here the kinetic energy is equal to 100 joules. 100 joules. And that equals 1/2 mv squared, just like we just solved. And if you solve for v, the mass is 1 kilogram. So the velocity in the horizontal direction will be, if you solve for it, 14.1 meters per second. Instead of going straight down, now it's going to be going in the horizontal to the right. And the reason why I said it was ice is because I wanted this to be frictionless, and I didn't want any energy lost to heat or anything like that. And you might say, okay, Sal, that's kind of interesting, and you kind of got the same number. Then with velocity, if I just drop the object straight down, that's interesting. But what else can this do for me? And this is where it's really cool. Not only can I figure out the velocity right at when all the potential energies disappear, but I can figure out velocity at any point, and this is fascinating, along this line. So let's say when the box is sliding down here. So let's say the box is at this point. It's slightly different, it changes colors too as it falls. So this is the 1 kilogram box, right? Falls and slides down here. Let's say at this point, its height above the ground is 5 meters. So what's its potential energy here? So let's just write something. All the energy is conserved, right? So the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy, right? I'm just saying energy is conserved here. Up here, what's the initial total energy in the system? Well, the potential energy is 100, and the kinetic energy is 0. It's stationary. I haven't dropped it. I haven't let go of it yet. It's just stationary. So the initial energy is going to be equal to 100 joules. This is 0. This is 100. So the initial energy is 100 joules. At this point, right here, what's the potential energy? Well, we're 5 meters up. So mass times gravity times height. Mass is 1 times gravity, 10 meters per second squared, times height times 5. So it's 50 joules. That's our potential energy at this point. And then we must have some kinetic energy going roughly, with the velocity going roughly in that direction, plus our kinetic energy at this point. And we know that no energy was destroyed, it's just converted. So we know the total energy still has to be 100 joules. So essentially what happened if we solve for this, very easy, it's effectively both sides. We know that the kinetic energy is now also going to be 50 joules. So what happened? Halfway down, essentially, half of the potential energy got converted to kinetic energy. And we can use this information, the kinetic energy is 50 joules, to figure out the velocity at this point. 1/2 mv squared is equal to 50. The mass is 1, multiply both sides by 2, you get v squared is equal to 100. The velocity is 10 meters per second along this crazy icy slide. And that is something that I would have challenged you to solve using traditional kinematics formulas, especially considering that we don't know really much about the surface of this slide. And even if we did, that would have been a million times harder than just using the law of conservation of energy, realizing that at this point, half the potential energy is now kinetic energy. It's going along the direction of the slide. I will see you in the next video.
Yes, okay.
Welcome back. I'll now do another conservation of energy problem. And this time I'll add another twist. So far, everything we've been doing, energy was conserved by the law of conservation. But that's because all of the forces that were acting in these systems were conservative forces. And now I'll introduce you to a problem that has a little bit of friction, and we'll see that some of the energy gets lost to friction. We can think about it a little bit, where does that energy go? So let's say, and I'm getting this problem from the University of Oregon, it says zebu.uoregon.edu. And they seem to have some light physics problems, so I'll use theirs, and I just want to make sure they get credit. So let's see, they say a 90 kilogram bike and rider, so the bike and rider combined are 90 kilograms, which is the mass. Is 90 kilograms. 90 kilograms. Start at rest from the top of a 500-meter long hill. Okay, so I think they mean that the hill is something like this. So this is the hill. That the hypotenuse here is 500 meters long. So the length of that, this is 500 meters. 500-meter long hill with a 5-degree incline. So this is 5 degrees. 5 degrees. You can kind of just do it like a wedge, like we've done in other problems. Pretty straight. Okay. Assuming an average friction force of 60 newtons. Okay, so they're not telling us the coefficient of friction, and then we have to figure out the normal force and all of that. They're just telling us what is the drag of friction, or how much is actually friction acting against this rider's motion. We can think a little bit about where that friction is coming from. So the force of friction is equal to 60 newtons, and of course it's going to be going against his motion or her motion. And the question asks us, find the speed of the biker at the bottom of the hill. So the biker starts up here, stationary. That's the biker, my very artful rendition of the biker. And we need to figure out the velocity at the bottom. So let's figure out, this to some degree is a potential energy problem. Well, it definitely is a potential, a mechanical law. It's definitely a conservation of mechanical energy problem. So let's figure out what the energy of the system is when the rider starts off. So the rider starts off at the top of this hill, so we definitely some potential energy, and is stationary, so there's no kinetic energy. So all of the energy is potential, and what is the potential energy? Well, it's potential energy is equal to mass times the acceleration of gravity times height, right? Well, that's equal to, the mass is 90, acceleration of gravity is 9.8 meters per second squared. And then what's the height? Well, here we're going to have to break out a little trigonometry. We need to figure out this side of this triangle. Consider this like a triangle. Let's see, we want to figure out the opposite. We know the hypotenuse, and we know this angle here. So the sine of this angle is equal to opposite over hypotenuse. So SOH. Sine is opposite over hypotenuse. So we know that the height, so we don't need to do a little work here. We know that sine 5 degrees is equal to the height over 500. Or that the height is equal to 500 sine 5 degrees. And I calculated the sine of 5 degrees ahead of time. Let me make sure I still have it today. But you could do this on your own. So this is equal to 500. Sine of 5 degrees is 0.087. So we multiply these out. What do I get? I'm using the calculator on Google actually. 500 times sine, you get 43.6. So this is equal to 43.6.
Oh, 0.
So the height, we calculate 500. Sine of 5 degrees is 0.087. So you multiply these out. What do I get? I'm using the calculator on Google actually. 500 times sine. You get 43.6. So this is equal to 43.6. So the height of the hill is 43.6 meters. So going back to the potential energy, we have the mass times the acceleration of gravity times the height times 43.6. And this is equal to, I can use my regular calculator, so I don't have to figure out trig functions anymore. So 90 times 9.8 times 43.6 is equal to, let's see, 38,400, roughly 38,455. So this is equal to 38,455 joules or newton meters. That's a lot of potential energy. So what happens at the bottom of the hill? I'm sorry, I have to readjust my chair. At the bottom of the hill, all of this gets converted to kinetic, or maybe I should pose that question. Does all of it get converted to kinetic energy? Almost. We have a force of friction here. And friction, you can kind of view friction as something that eats up mechanical energy.
or you could, these are also called non-conservative forces, because when you have these forces at play, all of the force is not conserved. So a way to think about it is that an energy, let's just call it total energy. So let's say total energy initial, well, let me strike initial energy is equal to the energy wasted in friction. Energy wasted in friction. I mean, wasted. I should have written just letters. From friction. Plus final energy. So we know what the initial energy is in this system. That's the potential energy of this bicycle. So that's, this roughly 38.5 kilojoules, or 38,500 joules roughly. And now let's figure out the energy wasted from friction, or how much, essentially, and the energy wasted from friction is the negative work that friction does. And what does negative work mean? Well, the bicyclist is moving 500 meters in this direction. So distance is 500 meters. But friction isn't acting along the same direction as distance. Friction is, the whole time friction is acting against distance. So when the force is going in the opposite direction as the distance, your work is negative. So in this case, we can say the work of friction. So another way of thinking of this problem is energy initial is equal to the, or you could say the energy initial plus the negative work of friction, right? If we say that this is a negative quantity, that this is equal to the final energy. And here I took the friction and put it on the other side because I said this is going to be a negative quantity in the system. And so you should always just make sure that this is a negative quantity. So when the force is going in the opposite direction as the distance, your work is negative. So in this case, we could say the work of friction. So another way of thinking of this problem is energy initial is equal to the, or you could say the energy. Energy initial plus the negative work of friction, right? If we say that this is a negative quantity, that this is equal to the final energy. And here I took the friction and put it on the other side because I said this is going to be a negative quantity in the system. And so you should always just make sure that if you have friction in the system, just as a reality check, that your final energy is less than your initial energy. Our initial energy is this 38, let's just say 38.5 kilojoules. What is the negative work that friction is doing? That's 500 meters, and the entire 500 meters, it's always pushing back on the rider with a force of 60 newtons. So force times distance, so it's minus 60 newtons, because going in the opposite direction of the motion, times 500. And this is going to equal the ending, this is going to equal the final energy. V8, it's always pushing back on the rider with a force of 60 newtons. So force times distance, so it's minus 60 newtons, because going in the opposite direction of the motion, times 500. And this is going to equal the ending, this is going to equal the final energy, right? And what is this? 60 times 500, that's 3,000. No, 30,000. Right? So let's subtract 30,000 from 38,500. Minus 30. I didn't have to do that. I can do that in my head. So that gives us 8,455 joules is equal to the final energy. And what is all the final energy? Well, by this time, the rider's gotten back to, I guess we call the sea level. So all of the energy is now going to be kinetic energy, right? What's the formula for kinetic energy? It's 1/2 mv squared. And we know what m is. The mass of the rider is 90. So we have, this is 90. If we divide both sides, so 1/2. And so what's the formula for kinetic energy? It's 1/2 mv squared. And we know what m is. The mass of the rider is 90. So we have, This is 90. So if we divide both sides, so 1/2 times 90, that's 40.
Uh,
45. So 8455 divided by 45. So we get b squared is equal to 187.9. Let's take the square root of that. We get so 8455 divided by 45. So we get b squared is equal to 187.9. Let's take the square root of that. We get the velocity 13.7. So the final velocity, so if we take the square root of both sides of this, so the final velocity is 13.7, and you can't read that, 13.7 meters per second. And this was a slightly more interesting problem because here we had a good bit of the energy wasn't completely conserved. Some of the energy, you could say, was eaten by friction. And actually that energy didn't disappear to a vacuum. It was actually generated into heat. And that makes sense. If you slid down a slide of sandpaper, your pants would feel very warm by the time you got to the bottom of that. But the friction of this, they weren't specific on where the friction came from, but it could have come from the gearing within the bike. It could have come from the wind. Maybe the bike actually skated a little bit on the way down. I don't know. But hopefully you found that a little bit interesting, and now you can not only work with conservation of mechanical energy, but you can work with problems where there's a little bit of friction involved as well. Anyway, I'll see you in the next video. Let's learn a little bit about springs. So let's say I have a spring. That's the floor. I have a spring. It's along the floor. Let's see the spring looks something like this. The spring looks like this. This is a nice spring. An amazingly drawn spring. Let's say at this end it's attached to a wall. It's a wall. And I know that, and so this is a spring when I don't have any force acting on it. This is just the natural state of the spring. And we can call this where it just naturally rests, this tip of the spring. And let's say that when I were to apply a force of, I don't know, 5 newtons into the spring, it looks something like this. Redraw everything. So when I apply a force of 5 newtons, when I apply a force of 5 newtons, the spring looks like this. Compresses, right? We're all familiar. We sit on a bed every day or something. So let's say it compresses to here. Oops. So if this was the normal resting, so this is where the spring was when I applied no force. When I apply 5 newtons, so I applied 5 newtons in that direction. 5 newtons. Let's say that this distance right here is, I don't know, let's say this was 10 meters. 10 meters. And so a typical question that you'll see, and then we'll explain how to do it, is, a spring compresses or, elongates when you apply a certain force by some distance. How much will it compress when you apply a different force? So my question is, how much will it compress when I apply 10 Newton force? So your intuition that it'll compress more is correct, but is it, linear to how much I compress it? Is it a square of how much I compress it? Well, how does it really? So your intuition that it'll compress more is correct, but is it, do it, is it this distance right here is, I don't know, let's say this was 10 meters. 10 meters. And so a typical question that you'll see, and then we'll explain how to do it, is, a spring compresses or, elongates when you apply a certain force by some distance. How much will it compress when you apply a different force? So my question is, how much will it compress when I apply 10 Newton force? So your intuition that it'll compress more is correct, but is it, linear to how much I compress it? Is it a square of how much I compress it? Well, how does it relate? You probably guess. It's actually worth an experiment. We can just keep watching the video. So let's say I apply 10 Newton force. What will the spring? Well, it'll be more compressed. Okay. 10 Newtons. 10 Newtons. And if this was the natural place where the spring would rest, what is this distance? Well, it turns out that it is linear. What do I mean by linear?
Well, it means that the more the force, it's equally proportional to how much the spring will compress. And it actually works the other way. If you applied 5 newtons in this direction to the right, you would have gone 10 meters in this direction. So it goes whether you're elongating the spring or compressing the spring within some reasonable tolerance. We've all had this experience. If you compress something too much or you stretch it too much, it doesn't really go back to where it was before. But within some reasonable tolerance, it's proportional. So what does that mean? That means that the restoring force of the spring, is minus some number times the displacement of the spring. So what does this mean? So in this example right here, what was the displacement of the spring? Well, if we take positive x to the right and negative x to the left, within some reasonable tolerance, it's proportional. So what does that mean? That means that the restoring force of the spring, force of the spring is minus some number times the displacement of the spring. So what does this mean? So in this example right here, what was the displacement of the spring? Well, if we take positive x to the right and negative x to the left, the displacement of the spring is what? The displacement in this example right here, x is equal to minus 10, right? So I'm at 10 to the left. And so it says that the restorative force is going to be equal to going to be equal to minus k times how much it's distorted times minus 10. So the minuses cancel out. So it equals 10k. What's the restorative force in this example? Well, you might say it's 5 newtons because that's the only force I've drawn here. And you would be to some degree correct. And actually, since we're doing positive and negative, and this 5 newtons is to the left, so it's in the negative x direction, I should call this minus 5 newtons. And I should call this minus 10 newtons because you see these are vectors. They're going to the left, and I'm picking a convention that to the left means negative. So what's the restorative force? Well, in this example, and we assume that k is a positive number for our purposes. In this example, the restorative force is a positive number. So what is the restorative force? So that's actually the force, the counteracting force of the spring. That's what this formula gives us. So if this spring is stationary when I apply this 5 Newton force, that means that there must be another equal and opposite force that's positive 5 newtons, right? If there weren't, the spring would keep compressing. And if the force was more than 5 newtons, the spring would go back this way. So the fact that I know that when I apply a 5 Newton force to the left, or it's the shaping force of the spring, that's what this formula gives us. So if this spring is stationary when I apply this 5 Newton force, that means that there must be another equal and opposite force that's positive 5 newtons, right? If there weren't, the spring would keep compressing. And if the force was more than 5 newtons, the spring would go back this way. So the fact that I know that when I apply 5 Newton force to the left, or a negative 5 Newton force, the spring is no longer moving. It means that there must be, or no longer accelerating actually. It means that there must be an equal and opposite force to the right. And that's the restorative force. Another way to think about it is if I were to let, well, I won't go there now. So in this case, the restorative force is 5 newtons. So we can solve for k. We can say 5 is equal to 10k. Divide both sides by 10. You get k is equal to 1/2. So now we can use that information to figure out what is the displacement when I apply a negative 10 Newton force, when I push the spring in with 10 newtons in the leftward direction. So first of all, what's the restorative force here? Well, if the spring is no longer accelerating in either direction, or the tip of the spring is no longer accelerating in either direction, we know that the restorative force must be counterbalancing this force that I'm compressing with, right? The force that the spring wants to expand back with is 10 newtons, positive 10 newtons, right? And we know the spring constant, this k, for this spring, for this material, whatever it might be, is 1/2. So we know the restorative force is equal to 1/2 times the distance, right? I know the formula is minus k, right? And then what is the restorative force in this example? It's 10 newtons. So we know that 10 newtons is equal to minus 1/2 x. And so what is x? We'll multiply both sides by minus 1/2. You get minus 20. I'm sorry, multiply both sides by minus 2. You get minus 20 is equal to x. It's minus 20. Whoops, minus 20. So x goes to the left 20 units. So that's all that it's telling. Oh, yes. And this law is called Hooke's law. It's named after, I'll read it, a physicist in the 17th century, British physicist. He figured out that the amount of force necessary
to keep a spring compressed is proportional to how much you've compressed it. And that's all that this formula says. And that negative number, remember, this formula gives us the restorative force. So it says that the force is always in the opposite direction of how much you displace it. So for example, if you were to displace the spring in this direction, if you were to apply a force and x were positive and you were to go in that direction, the force, oh wait, sorry, this was where this is where the spring rests. If you were to apply some force and take the spring out to here, this negative number tells us that the spring will essentially try to pull back with the restorative force in the other direction. Let's do one more problem, and I think this will be clear to you. So let's say I have a spring, and all of these problems kind of go along. So let's say when I apply a force of 2 newtons, so this is what I apply. When I apply a force of 2 newtons, let's say it this way. Let's say when I stretch the spring, let's say this is the spring. And when I apply a force of 2 newtons to the right, the spring gets stretched, I don't know. Let's say the spring gets stretched 1 meter. So first of all, let's figure out what K is. So if the spring is stretched by 1 meter out here, its restorative force will be 2 newtons back this way, right? So its restorative force is 2 newtons will equal minus K times how much I displaced it. If I displaced it by 1 meter, so then we get multiply both sides by -1. We get K is equal to -2. So then we can use Hooke's law to know the equation for this, figure out the restorative force for this particular spring would be -2x. And then I said, well, how much force would I have to apply to distort this spring by 2 meters? Well, it's for this, multiply both sides by -1. 2 newton. A is, figure out B2 this way, minus K times how much I displaced it. Well, I displaced it by 1 meter. So then we get multiply both sides by -1. We get A is equal to -2. So then we can use Hooke's law to know the equation for this, to figure out the restorative force for this particular spring would be -2x. And then I said, well, how much force would I have to apply to distort this spring by 2 meters? Well, it's 2 times 2 would be 4. 4 newtons to displace it by 2 meters. And of course, the restorative force will then be in the opposite direction. That's where we get the negative number. Anyway, I've run out of time. I'll see you in the next video. Welcome back. So we have this green spring here, and let's see, there's a wall here. There's a wall. And let's say that this is where the spring is naturally. So if I were not to push on the spring, it would stretch all the way out here. But in this situation, I've pushed on the spring, so it has a displacement of x to the left. And we'll just worry about magnitudes. We won't worry too much about direction. So what I want to do is think a little bit. Well, first I want to graph how much force I've applied at different points as I compress the spring. And then I want to use that graph to maybe figure out how much work we did in compressing the spring. So let's look at, I know I'm compressing to the left, maybe I should compress to the right so that you can, we'll just worry about the magnitude. So let's draw the right. Y-axis, x-axis. So this axis is how much I've compressed it, x, and then this axis, the y-axis, is how much force I have to apply. So when the spring was initially all the way out here. To compress it a little bit, how much force do I have to apply? Well, this was its natural state, right? And we know from, Hooke's law told us the restorative force, the restorative force, I'll write a R down here. The restorative force is equal to negative K, where K is the spring constant, times the displacement, right? That's the restorative force. So that's the force that the spring applies to whoever's pushing on it. The force to compress it is just the same thing, but it's going in the same direction as the x. If I'm moving the spring, if I'm compressing the spring to the left, then the force I'm applying is also to the left. So I'll call that the force of compression. The force of compression is going to be equal to K times x. And when the spring is compressed and not accelerating in either direction, the force of compression is going to be equal to the restorative force. So what I want to do here is plot the force of compression, force that the spring applies to whoever's pushing on it. The force to compress it is just the same thing, but it's going in the same direction as the x. So if I'm moving the spring, if I'm compressing the spring to the left, then the force I'm applying is also to the left. So I'll call that the force of compression. The force of compression is going to be equal to K times x. And when the spring is compressed and not accelerating in either direction, the force of compression is going to be equal to the restorative force. So what I want to do here is plot the force of compression with respect to x. Now this, I should have drawn it the other way, but I think you understand that x is increasing to the left in my example, right? This is where x is equal to 0. Let's say x is equal to 0 right here. This is x equals 0. And say, this might be x is equal to 10. So we've compressed it by 10 meters. So let's see how much force we've applied. So when x is 0, which is right here, how much force do we need to apply to compress the spring? Well, if we give 0 force, the spring won't move. But if we just give a little bit of force, if we just give like an infinitesimal, super small amount of force, we'll compress the spring just a little bit, right? Because at that point, the force of compression is going to be pretty much 0. So when the spring is barely compressed, we're going to apply a little bit of force. So almost at 0. Pretty much, but to displace the spring 0, we apply 0 force. To displace the spring a little bit, we apply a little bit more force. To displace the spring 1 meter, so if this is say 1 meter, how much force will we have to apply, I guess, to keep it there? So let's say if this is 1 meter. The force of compression is going to be K times 1, so it's just going to be K. Okay. And realize you didn't apply 0 and then apply K force. You keep applying a little bit more force. Every time you compress the spring a little bit, it takes a little bit more force to compress it a little bit more. So to compress it 1 meters, you need to apply K, and to get it there, you have to keep increasing the amount of force you apply. At 2 meters, you would have been up to 2K, etc. I think you see a line is forming. The line looks like something like that. And so this is how much force you need to apply as a function of the displacement of the spring from its natural rest state. And here I have positive x going to the right, but in this case, positive x is to the left. I'm just measuring its actual displacement. I'm not worried too much about direction. So I just want you to think a little bit about what's happening here. You just have to slowly keep on. You could apply a very large force initially. If you apply a very large force initially, the spring will actually accelerate much faster because you're applying a much larger force than its restorative force, and so it might accelerate into the spring bracket. Actually, we'll do a little example of that. But really, just to displace the spring a certain distance, you have to just gradually increase the force, just so that you offset the restorative force. Hopefully, that makes sense. If you understand that the force just increases proportional as a function of the distance, this is a linear equation. And what's the slope of this? Well, slope is rise over run, right? So if I run 1, this is 1. What's my rise? It's K. So the slope of this equation, the slope of this graph is K. So using this graph, let's figure out how much work we need to do to compress the spring. I don't know. Say this is x naught. So x is where it's a general variable. X naught is a particular. So using 1, that's my rise. It's K. So the slope of this equation. And what's the slope of this? Well, slope is rise over run, right? So if I run 1, this is 1. What's my rise? It's K. So the slope of this equation, the slope of this graph is K. So using this graph, let's figure out how much work we need to do to compress the spring. I don't know. Let's say this is x naught. So x is where it's a general variable. X naught is a particular value for x. That could be 10 or whatever. Let's see how much work it we need. So what's the definition for work? Is equal to the force in the direction of your displacement times the displacement, right? So let's see how much we've displaced. So when we go from 0 to here, we've displaced this much. And what was the force of the displacement? Well, the force was gradually increasing the entire time. So the force would be roughly about that big. I'm approximating. I'll show you that you actually have to approximate. So the force is kind of that square right there. And then to displace the next little distance, that's not bad enough. My force is going to increase a little bit, right? So this is the force, this is the distance. So if you see, the work I'm doing is actually going to be the area under the curve. Each of these rectangles, right? Because the height of the rectangle is the force I'm applying, and the width is the distance, right? So the work is just going to be the sum of all of these rectangles. And the rectangles I drew are just kind of approximations because they don't get right under the line. You have to keep making the rectangles smaller, and just sum up more and more rectangles, right? And actually, I'm touching on integral calculus right now. But if you don't know integral calculus, don't worry about it. But the bottom line is the work we're doing, hopefully I showed you, is just going to be the area under this line. So the work I'm doing to displace the spring, x meters, is the area from here to here. And what's that area? Well, this is a triangle, so we just need to know the base, the height, and multiply times 1/2, right? That's just the area of a triangle. So what's the base? So this is just x naught. What's the height? Well, we know the slope is k, so this height is going to be x naught times k. Whoops. So this point right here is the point x naught, and then x naught times k. And so what's the area under the curve, which is the total work I did to compress the spring x naught meters? Well, it's the base x naught times the height x naught times k, and then of course multiply by 1/2 to read dealing with the triangle, right? So that equals 1/2 k x naught squared. And for those of you who know calculus, that of course is the same thing as the integral of kx dx. It should make sense. It should be dx. But I don't want to go too much into calculus now. So that's the total work necessary to compress this spring by a distance of x naught, or if kx dx. It should make sense. It should be dx. But I don't want to go too much into calculus now. So that's the total work necessary to compress this spring by a distance of x naught. Or if instead of distance of x, you could just get rid of this naught. And why is that useful? Because the work necessary to compress the spring that much is also how much potential energy there is stored in the spring. So if I told you that I had a spring and it's by Hooke's, its spring constant. Its spring constant is 10, and I compressed it, I don't know, 5 meters. So x is equal to 5 meters. At the time that it is compressed, how much potential energy is in that spring? We could just say potential energy is equal to 1/2 k times x squared equals 1/2 k is 10 times 25. And that equals 125. And of course, work and potential energy are measured in joules. So this is really what you just have to memorize, or hope you don't memorize, if you understand where I got it. That's why I spent 10 minutes doing it. But this is how much work is necessary to compress a spring to that point, and how much potential energy is stored once it is compressed to that point, or actually stretched that much. It also, we've been compressing, we can also stretch the spring. And if you know that, then we can start doing some problems with potential energy in springs, which I will do in the next video. See you soon. Welcome back. So let's do a potential energy with problem with a compressed spring. So let's make this an interesting problem. So let's say I have a loop-de-loop made out of ice. I made it out of ice so that we don't have friction. Let me draw my loop-de-loop. There is the loop. There's the loop. All right. And let's say this loop-de-loop has a radius of 1 meter. So this is this right here. Is 1 meter. And so of course the loop-de-loop is 2 meters high. 2 meters high. And let's say I have a spring here. It's a compressed spring. This is the wall. This is my spring compressed. It's all tight like that. And let's say its spring constant, K, is, I don't know, 10. Attached to that compressed spring, so I have a block of ice. I need ice on ice, so I have no friction. Here's my block of ice. Shiny. And let's say the block of ice is, I don't know, 4 kilograms. 4 kilograms. And we also know that we are on Earth. That's important. This probably might have been different if we were on another planet. And my question to you is, how much do we have to compress the spring? So, let's say that the spring's natural state was here, right? If we didn't push on it, and now it's here. So what is this distance? How much do I have to compress this spring in order for when I let go of the spring, the block goes with enough speed and enough energy that it's able to complete the loop-de-loop and reach safely to the other end. So how do we do this problem? Well, in order to, any loop-de-loop problem, the hard part is completing the high point of the loop-de-loop. Right? The hard part is making sure you have enough velocity at this point so that you don't fall down. Your velocity has to offset the downward acceleration, in which case, and here is going to be the centripetal acceleration, right? So that's one thing to think about. And you might say, wow, this is complicated. I have a spring here. It's going to accelerate the block, and then the block's going to get here. Then it's going to decelerate. This is probably where it's going to be the slowest. Then it's going to accelerate back here. It's a super complicated problem. And in physics, whenever you have these super complicated problems, it's probably because you are approaching it in a super complicated way, but there might be a simple way to do it, and that's using energy, potential and kinetic energy. And what we learned when we learned about potential and kinetic energy is that the total energy in the system doesn't change it just gets converted from one form to another. So it goes from potential energy to kinetic energy, or to heat. And we assume that there's no heat because there's no friction. So let's do this problem. So what we want to know is how much do I have to compress the spring? So what I'm essentially saying is how much potential energy do I have to start off with with this compressed spring in order to make it up here? So what's the potential energy? Let's say I compress the spring X meters. So I compress the spring X meters. And in the last video, how much potential energy would I then have? Well, we learned that the potential energy of a compressed spring, and I'll call this the initial potential energy, with an I, is equal to 1/2 kx squared. And we know what k is. I told you that the spring constant for this spring is 10. So my initial potential energy is going to be 1/2 times 10 times x squared. So 10x squared. So what are all of the energy components here? Well, obviously at this point, the block's going to have to be moving in order to not fall down. So it's going to have some velocity, v. It's going tangential to the loop. And it also is going to have some potential energy still. And where's that potential energy coming from? Well, it's going to come because it's up in the air. It's above the surface of the loop-to-loop. So it's going to have some gravitational potential energy, right? So at this point, we're going to have some kinetic energy. We'll call that, well, I'll just call that kinetic energy final. This is what we care about. I'll maybe here, kinetic energy final. But I'll just define this as kinetic energy final. And then plus the potential energy final. And that, of course, has to add up to energy squared. And this, of course, now, this was kind of called the spring potential energy, and now this is gravitational potential energy. So what's the energy at this point? Well, what's kinetic energy? Kinetic energy final is going to have to be 1/2 times the mass times the velocity squared, right? And then what's the potential energy at this point? It's gravitational potential energy, so it's the mass times gravity times this height. So potential energy final is going to be mass times gravity times the height, which also stands for Mass General Hospital. Well, you can tell my wife's a doctor, so my brain just. It's gravitational potential energy, so it's the mass times gravity times this height. So potential energy final is going to be mass times gravity times the height, which also stands for Mass General Hospital. Well, you can tell my wife's a doctor, so my brain just. Anyway. So let's figure out the kinetic energy at this point. So what does the velocity have to be? Well, we have to figure out what the centripetal acceleration is. Well, and then given that, we can figure out the velocity, because we know that the centripetal acceleration, I'll change colors for variety. Centripetal acceleration, it has to be the velocity squared over the radius, right? Or we could say, and what is the centripetal acceleration at this point? Well, it's just the acceleration of gravity, 9.8 meters per second squared. So 9.8 meters per second squared is equal to v squared over r. And what's the radius of this loop? Well, it's 1. So v squared over r is just going to be equal to v squared. So v squared equals 9.8. We can take the square root, or we could just substitute the 9.8 straight into this equation, right? So the kinetic energy final is going to be equal to 1/2 times the mass times 4 times v squared times 9.8. And that equals, let's just use g for 9.8, because I think that might keep it interesting. So this is just g, right? So it's 2 times g. So the kinetic energy final is equal to 2g, and g is normally kilogram meters per second squared, but now it's energy, right? So it's going to be in joules. There's 2g, right? And what is the potential energy at this point? What's the mass, which is 4 times g, times the height, which is 2. So it's equal to 8g, right? So what's the total energy at this point? The kinetic energy is 2g, the potential energy is 8g, so the total energy at this point is 10g. 10g total energy, 10g. So the total energy at this point is 10g, and we didn't lose any energy to friction and heat and all of that. So then the total energy at this point has also got to equal 10g. And at this point, we have no kinetic energy because this block hasn't started moving yet. So all of the energy is the potential energy. So this also has to equal 10g. And this g I keep saying is just 9.8. I just wanted to do that just so you see that it's a multiple of 9.8, just for you to think about. So what do we have here? Well, these numbers worked out well. So let's divide both sides by 10, and you get x squared is equal to g, which is 9.8. So the x is going to be equal to the square root of g, which is going to be equal to, let's see, I think 9.8. The square root of it, it's 3.13. So x is 3.13. So we just did a fairly, what seemed to be a difficult problem, but it wasn't so bad. We just said that we'll do the energy in the beginning has to be the energy at any point in this, assuming that none of the energy is lost to heat. so we just figured out that if we compress this spring with a spring constant of 10, if we compress it 3.3 meters, 3.13 meters, we will have created enough potential energy, and in this case, the potential energy is 10 times 9, so roughly 98 joules of potential energy to carry this object all the way with enough velocity at the top of the loop to complete it and then come back down safely. And so if we want to think about it, what's the kinetic energy at this point? Well, we figured out it was 2 times g, so it's like 19.6 joules. What is it? 9.6. Right. And then at this point, it is 98 joules. Right? Did I do that right? Well, anyway. Well, I'm running out of time, so I hope I did do the last part right. But I'll see you in the next video.
About 9 years late. Okay.
What's a conservative force? Conservative forces are any force wherein the work done by that force on.
Hold on. I need to go. I need to pee. Why do I have to have a bladder? Why do I have to sleep? There we go.
What's a conservative force? Conservative forces are any force wherein the work done by that force on an object only depends on the initial and final positions of the object. In other words, the work done by a conservative force on a mass does not depend on the path taken by that mass. If the work done by a force follows this rule, then we call it a conservative force. For instance, the gravitational force on a 5 kilogram mass is 49 newtons. If the mass moves downward by an amount of 6 meters, the work done by gravity is going to be 294 joules. Now let's start over. Say the mass again moves down 6 meters, but then it moves up 6 meters, then down again 6 meters. The work done by gravity for the first downwards trip was 294 joules. Then for the upwards trip, since the gravitational force is pointing in the opposite direction of the motion of the mass, the work done by gravity is going to be negative 294 joules. Then for the last trip downwards, the work again is positive 294 joules. That means that the total work done on the mass from gravity is still 294 joules, just like it was when the mass was lowered only once. In other words, the work done by the gravitational force doesn't depend on the specifics of the path taken by the mass. The work done by gravity only depends on the initial and final position of the mass. In fact, you could allow the mass to take any path from this initial point to the final point, and the work done by gravity is still just going to be 294 joules.
Wow.
Because the work done by gravity doesn't depend on the path taken, we call gravity a conservative force. The force exerted by a spring is another example of a conservative force. The total work done on a mass by a spring does not depend on the path taken by the mass. It only depends on the initial and final positions of the mass. The term conservative comes from the fact that conservative forces conserve mechanical energy, whereas non-conservative forces do not conserve mechanical energy. Mechanical energy is kinetic energy and potential energy. An example of a non-conservative force is friction. If I move up, forces do not conserve mechanical energy by the mass. It only depends on the initial and final positions of the mass. The term conservative comes from the fact that conservative forces conserve mechanical energy. Whereas non-conservative forces do not conserve mechanical energy. Mechanical energy is kinetic energy and potential energy. An example of a non-conservative force is friction. If I move a mass along a table from point A to point B, friction does a certain amount of negative work on the mass, which creates some thermal energy. If instead of going straight from A to B, I make the block go from A to B back to A over and over again, the work done by friction will become larger and larger, and it'll generate more and more thermal energy. Because the work done by friction depends on the path taken, friction is not a conservative force. Similarly, air resistance is not a conservative force, since the work done by air resistance depends on the specifics of the path taken. It's useful to note that if a force is conservative, you could define a potential energy for that force. That's why conservative forces like gravity and spring forces have potential energies associated with them. And non-conservative forces like friction do not have potential energies associated with them. This makes sense because if you do work against the gravitational force by lifting a mass in the air, you can get that energy back out by letting the mass fall down, turning potential energy into kinetic energy. Similarly, if you do work against the spring force by compressing a spring, you can get that energy back out by letting the spring decompress, which turns the stored potential energy into kinetic energy. But if you do work against the force of friction, you'll have a hard time trying to get that energy back out. The energy has been dissipated into the form of thermal energy and is now randomly distributed along the ground and into the block.
Alright, let's look at that minute. Yeah. Yeah. Okay, let's take a 10-minute. You're doing okay. Just gonna have to get to 9. Just have to get to 9. I think we can make it.
equal to instantaneous power at any moment. And that means work per time gives you both the average power and the instantaneous power in this case. Let's say you weren't so lucky and the instantaneous power was changing as the car progressed. Then how would you find the instantaneous power? Well, we know that power is just the work per time. So something we can try is to plug in the formula for work, which looks like FD cosine theta.
What color is it again?
You have to hit it first.
Oh,
Yeah.
And then divide by the time. Something that you might notice is that now we have distance per time in this formula. So let's isolate the distance per time. Distance per time is just the speed, so I can replace d over t with v in this formula. And if you plug in the instantaneous speed of the car at a given moment in time, you'll be finding the instantaneous power output by the force on the car at that particular moment in time. So to find the instantaneous power output by a force, plug in the force on the object at a particular moment in time, multiply by the speed of the object at that same moment in time, then multiply by cosine theta, but be careful here, theta isn't any old angle, it's the angle between the force on the object and the velocity of the object. But in many cases, the force is in the same direction as the velocity, which means the angle between the force and the velocity is 0. And since cosine of 0 is 1, you don't really need the cosine in the formula at all. And you find that the instantaneous power is just the force times the speed. All right, so what does power mean? Power is the rate at which work is done. What does average power mean? Average power is the work done divided by the time interval that it took to do that work. What does instantaneous power mean? Instantaneous power is the power output of a force at a particular moment in time.
Welcome back. We'll now use a little bit of what we've learned about work and energy and the conservation of energy and apply it to simple machines, and we'll learn a little bit about mechanical advantage. So I've drawn a simple lever here, and you've probably been exposed to simple levers before. They're really just kind of like a seesaw. This place where the lever pivots, this is called the fulcrum. That's where the pivot point. You can kind of view this as either a seesaw or a big plank of wood on top of a triangle, which essentially is what I've drawn. So in this example, I have the big plank of wood. At one end, I have this 10 Newton and what we're going to figure out is, one, how much force, well, we can figure out a couple of things. How much force do I have to apply here to just keep this level, right? Because this weight's going to be pushing on that and downward, so it would naturally want this whole lever to rotate clockwise. So what I want to figure out is how much force do I have to apply to either keep the lever level or to actually rotate this lever counterclockwise. And when I rotate the lever counterclockwise, what's happening? I'm pushing down on this left-hand side and I'm lifting this 10 Newton block. So let's do a little thought experiment and see what happens after I rotate this lever a little bit. So let's say this is what I've drawn here in mauve. That's our starting position. And in yellow, I'm going to draw the finishing position. So the finishing position is going to look something like this. Finishing position, something like this. Oh, and also one thing I want to figure out, I wanted to, right, is let's say that this distance right here from where I'm applying to the force, where I'm applying the force to the fulcrum, let's say that distance is 2. That distance is 2. And from the fulcrum to the weight that I'm lifting, that distance is 1. Let's just say that, just for the sake of argument. Let's say it's 2 meters and 1 meter. Well, there could be 2 kilometers and 1 kilometer. So and what I did is I pressed down with some force and I rotated it through an angle theta. Right? So that's theta, then this is also theta. So my question to you, and we'll have to take out a little bit of our trigonometry skills, is how much did this object move up? So essentially, what was this distance? What's its distance in the vertical direction? How much should it go up? And also, for what distance did I have to apply the force downwards here? So that's this distance, in order for this weight to move up this distance over here. So let's figure out either one. So this distance is what? Well, we have theta. This is the opposite. This is a 90-degree angle, right? We started off at level. So this is opposite, and this is what? This is the adjacent angle, right? So what do we have there? Opposite over adjacent. So opposite over adjacent. Opposite over adjacent. That's TOA, or tangent. So in this situation, we know that the tangent of theta is equal to, let's call this the distance the object, the distance but we move the weight, right? So that equals opposite over adjacent, the distance, but we move the weight over 1, right? And then if we go on to this side, we can do the same thing. Tangent is opposite over adjacent. So this is, let's call this the distance of the force. So here the opposite is the distance of the force. The adjacent is this 2 meters, right? This is the hypotenuse right here. So we also have the tangent of theta, that I use this triangle, is equal to the opposite side, distance of the force over 2 meters. So this is interesting. They're both equal to tangent of theta. So you don't even have to figure out what the tangent of theta is. We know that this quantity is equal to this quantity, right? And we can write it here. We can write the distance of the force, that's the distance that we have to push down on the side of the lever downwards, over 2 is equal to the distance of the weight. The distance the weight traveled upwards is equal to the distance of the weight divided by 1. Or we could say this 1 we could ignore, right? We can divide by just 1, or we could say the distance of the force is equal to 2 times the distance of the weight. And this is interesting, because now we can apply what we just learned here to figure out what the force was. And how do I do that? Well, when I'm applying a force here over some distance, I'm putting energy into the system. I'm doing work. Work is just the transfer of energy into this machine. And when I do that, that machine is actually transferring that energy to this block. It's actually doing work on the block by lifting it up. So we know the law of conservation of energy, and we're assuming that this is a frictionless system and that nothing is being lost to heat or whatever else. So the work in has to be equal to the work out. And so what's the work in? Well, it's the force that I'm applying downward times the distance of the force. So this is the work in, force times the distance of the force. I'm going to switch colors just to keep things interesting. And that has to be the same thing as the work out, right? Well, what's the work out? Well, it's the force of the weight pulling downwards, right? So we have to, it's essentially the lifting force of the lever, right? You have to counteract the force of the weight pulling downwards. Actually, sorry, I said it a bit. But so this lever is essentially going to be pushing up on this weight, right? The weight ends up here. So it pushes up with a force equal to the weight of the object. So that's the weight of the object, which is, I said it was a 10 Newton object, right? So it's 10 Newtons. That's the force, the upward force here, and it does that for a distance of 1. Well, we figured out this object, this weight, moves up with the distance d sub w times d sub w, right? And we know what the distance of the force is in terms of the distance of w. So we could rewrite this as force times, substitute here, 2 dw is equal to 10 dw. Divide both sides by 2, and you have, or actually divide both sides by 2 dw, and you get force is equal to 10 dw over 2 dw, which is where the w's cancel out, you're just left with 5. So this is interesting, and I think you'll see where this is going. We did a little complicated this time, but hopefully you'll realize a general theme. This was a 10 Newton weight, and I only had to press down 5 Newtons in order to lift it up. But at the same time, I pressed down with 5 Newtons, but I had to push down for twice as long. So my force was half as much, but my distance that I had to push was twice as much. And here, it's the opposite. The distance is twice as much. The force is twice as much, but the distance it traveled is half as much. And what essentially just happened here is I multiplied my force. And because I multiplied my force, I essentially lost some distance. Well, I multiplied my force because I inputted a 5 Newton force, and I got a 10 Newton force out, although the 10 Newton force traveled for less distance because the work was constant. And this is called mechanical advantage. If I have an input force of 5 and I get an output force of 10, the mechanical advantage is 2. The mechanical advantage is equal to output force over input force. And that should hopefully make a little bit of sense to you. And another thing that maybe you're starting to realize now is that proportion. The proportion of the mechanical advantage was actually the ratio of this length to this length. And we figured that out by taking the tangent and doing these ratios. But in general, it makes sense because this force times this distance has to be equal to this force times this distance. And we know that the distance this goes up is proportional to the length of this from the fulcrum to the weight. And we know on this side, the distance that you're pushing down is proportional to the length from where you're applying the weight to the fulcrum. And now I'll introduce you to a concept of moments in just a moment. So in general, if I have, and this is really all you have to learn, that last thought exercise will just kind of show it to you. If I have a fulcrum here, and if we call this distance d1, and we call this distance d2, and if I have a force, if I want to apply an upward force here, let's call this F1, and I have a downward force F2. In this machine, F2 times d2 is equal to d1 times F1. And this is really all you need to know. And this just all falls out of
The work in is equal to the work out. Now this quantity isn't exactly the work in. The work in is this force, sorry, F2, is this force times this distance. But this distance is going to be proportional to this distance. And that's what you need to realize. And this quantity right here is actually called the moment. In the next video, which I'll start because very soon it's about to end at that time, I will use these quantities to solve a bunch of mechanical management problems. See you soon.
Oh, you practice test?
Yeah,
For what?
basically.
Oh, you have to take one now?
I want to. I don't have anything else to do.
Okay.
Might as well.
Yeah.
I don't have any room here. So
Oh, okay.
I'll go.
I think I'm gonna actually. I think before I go into lesson 6, I want to work out what they want to work out.
Me?
Yeah,
How?
I should work out the room.
So?
You don't have to.
Oh, you want me to do the spots?
No, you don't have to. I'm just saying I'm gonna work out for like 10, 15 minutes, and then I'll do lesson 6. But if you want to do this, you
Welcome back. In the last, let's say
It's not bad. Seven something plus the article. Yeah, I think we can. All right, let me just let's reset. Let's reset. Let me exercise real quick, and then we'll hit 6, and hopefully we still have time for sum of 7. But looks like we'll finish 8 and 9 early tomorrow morning. I don't want to stay up too late, so yeah. So we'll do the 7, right? Are we on 7? No, we're not on 7. We're on 6, but 7, 8. Oh, maybe we can, like I said, maybe we can do sum of 7. I don't know. Let's see if we can finish 7. 5, 6, 7, 8, 10. Read some questions. Yeah, I don't know. We'll see. Oh, let me take it up there. I think it's too much time. It's just 15. go. Okay, let's source it out. Let's source out, and let's do this one. I want to do a sum of 7. Excuse me. Oh man, Riptide submersible. Wow. Yikes. Oh, that's true. Rip. I mean, I can't believe people were talking about this here though. I mean, this video was made 10 years ago, and there's people talking about this now. I'm like, wow.
fluids. So, and you probably have some notion of what a fluid is, but let's talk about it in the physics sense, or maybe in the chemistry sense, depending on in what context you're watching this video. So, fluid is anything that takes the shape of its container. So, for example, if I had I don't know, a glass sphere. Let's say that we're in like let's say I completely fill this glass sphere with water. Let's say we're in a zero gravity environment, but you really don't even need that. Let's say that every glass sphere, a glass sphere. Let's say that we're in like let's say I completely fill this glass sphere with water. Let's say we're in a zero gravity environment, but you really don't even need that. Let's say that every cubic centimeter, you really don't even need that. Completely fill this glass sphere with water. Let's say we're in a zero gravity environment, but you really don't even need that. Let's say that every cubic centimeter or cubic meter of this glass sphere is filled with water. And notice, and then let's say that if I were to, and let's say it's the sun. Let's say that we're, I don't know, a glass sphere. Let's say that we're in like let's say I completely fill this glass sphere with water. Let's say we're in a zero gravity environment, but you really don't even need that. Let's say that every cubic centimeter or cubic meter of this glass sphere is filled with water. And notice, and then let's say that if I were to, and let's say it's not glass, let's say it's a rubber sphere. If I were to change the shape of that sphere, but not really change the shape of the volume, if I were to change the shape of the sphere where it looks like this now, the water would just change its shape with the container, right? The water would just change the shape of the container. And in this case, I have green water. And the same is also true if I had
if that was oxygen or if that was just some gas, right? It would fill the container, and in this situation, it would also fill the newly shaped container. So a fluid, in general, a fluid takes the shape of container, takes shape of container. And I just gave you two examples of fluids. You have liquids, and you have gases. Those are two types of fluid. Both of those things take the shape of a container. And now what's the difference between a liquid and a gas then? Well, a gas is compressible, which means that I could actually decrease the volume of this container, and the gas will just become denser within the container. So you can think of it as, if I blew air into a balloon, you could squeeze that balloon a little bit. There's air in there. I mean, at some point, the pressure might get high enough to pop the balloon, but you can squeeze it. While a liquid is incompressible. And how do I know that a liquid is incompressible? Well, imagine the same balloon filled with water, completely filled with water. If you squeezed on that balloon from every side, so let's say that, let me pick a different color. Let's say that I have this balloon and it was filled with water. If you squeezed on this balloon from every side, you would not be able to change the volume of this balloon. Actually, no matter what you do, you would not be able to change the volume of this balloon, no matter how much force or pressure you put from any side on it. While if this was filled with gas, and magenta, balloon for gas, you actually could decrease the volume by just increasing the pressure on all sides of the balloon. And you can actually squeeze it and make them change the volume of this balloon, no matter how much force or pressure you put from any side on it. While if this was filled with gas, and magenta, balloon for gas, you actually could decrease the volume by just increasing the pressure on all sides of the balloon. And you can actually squeeze it and make the entire volume smaller. So that's the difference between a liquid and a gas. Gas is compressible, liquid isn't. And we'll learn later that you can turn a liquid into a gas and gas into a liquid and turn liquids into solids. But we'll learn all about that later. But this is a pretty good working definition of that. So let's use that. And now we're going to actually just focus on the liquids to see if we could learn a little bit about liquid motion or maybe even fluid motion. Well, a gas is compressible, which means that I could actually decrease the volume of this container, and the gas will just become denser within the container. So you can think of it as, if I blew air into a balloon, you could squeeze that balloon a little bit. There's air in there. I mean, at some point, the pressure might get high enough to pop the balloon, but you can squeeze it. While a liquid is incompressible. Incompressible. And how do I know that a liquid is incompressible? Well, imagine the same balloon filled with water, completely filled with water. If you squeezed on that balloon from every side, so let's say that, let me pick a different color. Let's say that I had this balloon and it was filled with water. If you squeezed on this balloon from every side, you would not be able to change the volume of this balloon. Actually, no matter what you do, you would not be able to change the volume of this balloon, no matter how much force or pressure you put from any side on it. While if this was filled with gas, and magenta, balloon for gas, you actually could decrease the volume by just increasing the pressure on all sides of the balloon. And you can actually squeeze it and make the entire volume smaller. So that's the difference.
Bye, guys.
A liquid and a gas. Gas is compressible, liquid isn't. And we'll learn later that you can turn a liquid into a gas and gas into a liquid and turn liquids into solids. But we'll learn all about that later. But this is a pretty good working definition of that. So let's use that. And now we're going to actually just focus on the liquids to see if we could learn a little bit about liquid motion or maybe even fluid motion in general. Okay, let me draw something else. So let's say I had a situation where, let's say I have this weird shaped object which tends to show up in a lot of physics books, which I'll draw in yellow. This weird shaped container where it's relatively narrow there, and then it goes and kind of U-turns into a much larger opening. The area of this opening is
Right.
let's say I have this weird shaped object which tends to show up in a lot of physics books, which I'll draw in yellow. Weird shaped container where it's relatively narrow there, and then it goes and kind of U-turns into
to a much larger opening. Let's say that the area of this opening is, let's say this is A1, and the area of this opening is A2. Right, and this one is bigger. And let's fill this thing with some liquid, which will be blue. So that's my liquid. Let's fill with some liquid. Let me see if they have this tool. There you go. Look at that. Fill it with liquid. So complete. All right. And this wasn't. And this was liquid. It's not just a fluid. And so what's the important thing about liquid is that it's incompressible. So let's take what we know about force, actually about work, and see if we can come up with any rules about force and pressure with liquids, etc. So what do we know about work? Work is force times distance, or you can also kind of view it as the energy put into the system. I'll write it down here. So work is equal to force times distance. And we learned in mechanical advantage, etc., that the work in, I, is equal to work out, right? The force times the distance that you put into a system is equal to the force times the distance you put out. And you might want to review the work chapters on that, but that's just the law of conservation of energy, because work in is just the energy that you're putting into a system, right? It's measured in joules, and work out is the energy that comes out of a system. And that's just saying that no energy is destroyed or created. It just turns into different forms. So let's just use this definition. So the force times distance in is equal to force times distance out. Force in, I'll divide like that, times distance in is equal to force out times distance out. All right, so let's say that I pressed with some force on this entire surface. So let's say I had like a, let's say it's like a piston. Let me see if I can draw a piston. It's a good color for piston. So let's add a magenta piston right here. And I push down on this magenta piston. Right there. So I pushed down on this with a force of F1, right? And let's say I push it a distance of D1. So let me say, so it goes, that's its initial position, and say its final position. I'll do in a, let's see what color. The hardest part of these videos is picking the color. So let's say like after I've pushed it, the piston goes this far. So this is the distance that I pushed it, right? So this is D1. The water is here, and I pushed the water down D1 meters, whatever, right? So in this situation, my work in is F1 times D1, right? Let me ask you a question. How much water did I displace? How much total water did I displace? What's this volume, right? I took this entire volume and pushed it down. So what's the volume right there that I displaced? Well, the volume there is going to be, so the volume that I'm displacing, so I'll say that the volume displaced has to equal this distance, right? This is like a cylinder of liquid, of liquid. So this distance times the area, right? Times the area of the container at that point. And I'm assuming it's constant at that point, then it changes after that. So it equals area 1 times distance 1, right? Well, we also know that that liquid has to go someplace, right? Because what do we know about a liquid is that you can't compress it. You can't change its total volume. So all of that volume is going to have to go someplace else. So this is where the liquid was. The liquid is going to rise some level. Let's say it gets to this level. This is its new level, right? It's going to change some distance here. It's going to change some distance there. And how do we know what distance that's going to be? Well, the volume that it changes here it's got to go someplace, right? You got to say, well, that's going to push on that. That's all going to push. And that liquid has to go someplace. And essentially it's going to end up, it might not be the exact same molecules, but that might displace some liquid here. That's going to displace some liquid here, here, and here, and here. And all the way until the liquid up here gets displaced and gets pushed upward. So the volume that you're pushing down here is the same volume that goes up right here. And so what's the volume? What's the change in volume? Or how much volume did you push up here? Well, this volume here is going to be the distance 2 times this larger area, right? So we could say volume 2 is going to be equal to the distance 2 times this larger area. And we know that this liquid is incompressible. So this volume has to be the same as this volume, right? So we know that these two quantities are equal to each other. So area 1 times distance 1, right? This area times this distance is going to be equal to this area times this distance. Area 2 times distance 2. So let's see what we can do. So we know this, that the force in times the distance in is equal to the force out times the distance out. Let's take this equation. I'm going to switch back to green just so we don't lose track of things. And divide both sides by, well, let's just rewrite it. So let's say I rewrote each input force. Oh, actually, I'm about to run out of time, so I'll continue this into the next video. See you soon. So just to review what I was doing in the last video before I run out of time. I said that
okay, conservation of energy tells us that the work I put into the system, or the energy that I put into the system, that's really the same thing, is equal to the work that I get out of the system, or the energy that I get out of the system, right? And I said, well, that means that the input work is equal to the output work, or that the input force times the input distance is equal to the output force times the output distance. That's just the definition of work. And let me just rewrite this equation here. If I could just rewrite this exact equation, I could say, so the force, input force, and let me just divide it by, just for kicks, let me divide it by this area. Because what I'm the input here, I'm pressing down this piston that's pressing down on this area of water. So it's input force, and let me say that, times the input area. Well, let me call this input. Let's call it the input 1. Let's call the output 2 for simplicity. So there's going to be some, let's say I have a piston on the top here. This brown is good. So I have another piston here. Right? And there's going to be some outward force, F2. And this is the general notion is that I'm pushing on this water. The water can't be compressed, so the water's going to push up on this end, right? So the input force times the input distance is going to be equal to the output force times the output distance, right? This is just law of conservation of energy and everything. So I just I'm rewriting this equation. So if I take the input force and divide by the input area, just switch back to green. And then let's say I multiply by the area then. And I just multiply times T1. See what I did here? I just multiplied and divided by A1, which you can do. You can multiply and divide by any number, right? These two cancel out. Is equal to the same thing on the other side. F2. I'm not good at managing the space. Like F2 over A2 times A2 times D2. Hopefully that makes sense. So what's this quantity right here? This F1 divided by A1. Well, force divided by area, if you haven't been familiar with it already, and actually if you're just watching my video, this is the reason for you to be, is defined as pressure. Pressure is force in a given area. So this is pressure. So we'll call this the pressure that I'm inputting into the system. Pressure 1 times, and what's area 1 times distance 1? So that's the area of the tube at this point, the cross-sectional area times its distance. Well, that's equal to this volume that I calculated in the previous video, right? We could say that's the input volume, or V1, pressure times V1, is equal to the output pressure, right? Force 2 divided by area 2, right? That's the output pressure that the water is exerting on this piston. So that's the output pressure, P2. And what's area 2 times D2? So this area, the cross-sectional area, times the height at which how much the water is being displaced upward, that is equal to volume 2, right? But what do we know about these two volumes? And I went over it probably redundantly in the previous video, is that those two volumes are equal, right? V1 is equal to V2. So we can just divide both sides by that equation, and you get the pressure input is equal to the pressure output. So P1 is equal to P2. So P1 is equal to P2. P2. And I did all of that just to show you that this isn't a new concept. This is just the conservation of energy. The only new thing I did is I divided, we have this notion of the cross-sectional area, and we have this notion of pressure. So where does that help us? Well, this actually tells us, and you can do this example in multiple situations, but I like to think of it if we didn't have gravity first, because gravity tends to confuse things. We'll introduce gravity in a video or two. Is that when you have any external pressure onto a liquid, so onto an incompressible fluid, that pressure is distributed evenly throughout the fluid. And that's what we essentially just proved just using the law of conservation of energy and everything we know about work. And what I just said, that's called Pascal's principle. That if any external pressure is applied to a fluid, that pressure is distributed throughout the fluid equally. And another way to think about it, I mean, we proved it with this little drawing here. Another way to think about it is, let's say that I have a tube, and the end of the tube is a balloon. Let's say I'm doing this on the space shuttle. And it's saying that if I increase, so let's say that I have some piston here, right? Let's say I were to, and this is stable, right? And let me say I have water throughout this whole thing. I have water throughout the whole piston. Let me see if I can fill function again. Oh no, there must have been a hole in my drawing. Let's draw the water. So I have water throughout this whole thing. And all Archimedes' principle, all Pascal's principle is telling us that if I were to apply some pressure, here, pressure in, that net pressure, so if I, and that pressure is going to, that extra pressure I'm applying is going to compress this a little bit. That extra compression is going to be distributed through the whole balloon. Let's say that this right here is rigid. Let's say that's kind of metal structure. The rest of the balloon is going to expand uniformly. So that pressure, that increased pressure I'm doing is going through the whole thing. It's not like the balloon will get, it's not like the balloon is just going to get longer, that the pressure is just translated down here, or that just up here the balloon's going to get wider and it's just going to stay the same like that. hopefully that gives you a little bit of intuition. But going back to what I had drawn before, that's actually interesting because that's actually another simple, maybe or maybe not so simple machine that we've constructed. And I almost defined it as a simple machine when I initially drew it. Right? Let's draw that weird thing again where it looks like this, where I have water in it. There's a bunch of water. Let's see. Try to fill it. So I can fill it. Completely filled. There you go. So this is cool because this is now another simple machine because we know that the pressure in, the pressure in is equal to the pressure out, right? Pressure in is equal to the pressure out, and pressure is just divided is force divided by area. So the force in divided by the area in is equal to the force out divided by the area out, right? So let's say let me give you an example. Let's say that I were to apply with a pressure of, let's say the pressure in is equal to 10 pascals. That's a new word. It's named after Pascal's principle, Blaise Pascal. And so, and what is a Pascal? Well, that is just equal to 10 newtons per meter squared. That's all a Pascal is. It's a newton per meter squared. It's a very natural. It's a very natural unit. So let's say my pressure in is 10 pascals, and let's say that my input area is 2 square meters. So if I look at the surface of the wall there, it would be 2 square meters. And let's say that my output area is equal to I don't know, 4 meters squared. So what would be so what I'm saying is I can push on a piston here, and that the water is going to push up with some piston here, right? So first of all, I told you what my input pressure is. What's my input force? Well, input pressure is equal to input force divided by input area. So 10 pascals is equal to my input force divided by my area. So I multiply both sides by 2. I get input force is equal to 20 newtons. So my question to you is, what is the output force? How much force is the system going to push upwards at this end? Well, we know that if my input pressure was 10 pascals, my output pressure would also be 10 pascals. So I also have 10 pascals is equal to my out force over my out cross-sectional area, right? So I'll have a piston here that goes up like that. And so that's 4 meters. So I do 4 times 10. So I get 40 newtons is equal to my output force. So what just happened here? I inputted, so my input force is equal to 20 newtons. And my output force is equal to 40 newtons. So I just doubled my force, or essentially I had a mechanical advantage of 2. So this is an example of a simple machine. And it's a hydraulic machine. Anyway, I've just run out. I'll see you in the next video. And my output force is equal to 4 newtons. So I just doubled my force, or essentially I had a mechanical advantage of 2. So this is an example of a simple machine. It's a hydraulic machine. Anyway, I've just run out. I'll see you in the next video. In the last video, we showed that any external pressure on a
liquid in a container is distributed evenly through the liquid. But that only applied to, and that was called Pascal's principle. But that only applied to external pressure. Let's think a little bit about what the internal pressure is within a liquid. And we're all familiar, I think, with the notion of the deeper you go into a fluid, or the deeper you dive into the ocean. In the last video, we showed that any external pressure on a liquid in a container is distributed evenly through the liquid. But that only applied to, and that was called Pascal's principle. But that only applied to external pressure. Let's think a little bit about what the internal pressure is within a liquid. And we're all familiar, I think, with the notion of the deeper you go into a fluid, or the deeper you dive into the ocean, the higher the pressure on it. So let's see if we can think about that a little bit more analytically and get a framework for what the pressure is at any depth under the water, or really in any fluid. So here I've drawn a cylinder, and in that cylinder I have some fluid. Let's not assume that it's water, some fluid. That's the blue stuff. And I'm also assuming that I'm doing this on a planet that has the same mass as Earth, but it has no atmosphere. So there's a vacuum up here. There's no air, and we'll see later. The atmosphere actually adds pressure on top of this. So assume that there's no air, but it's on the same mass as a planet of the same mass. So the gravity is the same. So one, there is gravity, so the liquid will fill this container on the bottom part of it. And also, the gravitational constant would be the same as Earth. So we can imagine this is a horrible situation where Earth has lost its magnetic field and solar winds have gotten rid of Earth's atmosphere. That's very negative. So but anyway, let's go back to the problem. Let's say within this cylinder, I have I don't know, like a thin piece of foil or something that takes up the entire area of the cross-sectional area of the cylinder. And I did that just because I want that to be an indicator of whether the fluid is moving up or down or not. So let's say I have that in the fluid at some depth h, and since the fluid is completely static, nothing's moving, that object that's floating right at that level, at a depth of h, will also be static. And in order for something to be static, or it's not moving, what do we know about it? Well, we know that the net forces on it must be zero. In fact, that tells us that it's not accelerating. And obviously, if something's not moving, it has a velocity of zero, and that's a constant velocity. So it's not accelerating in any direction. So its net forces must be zero. Right? So this force down must be equal to the force up. Right? So what is the force down? What is the force down acting on this cylinder? Well, it's going to be the weight of the water above it, right? Because we're in a gravitational environment, and so this water has some mass, and so whatever that mass is times the gravitational constant will equal the force down. So let's figure out what that is. So the force down, which is the same thing as the force up, is going to equal the mass of this water. Right? The mass of this water is going to equal the mass of that water times the gravitational constant. Oh, actually, I shouldn't say water. I'm using the let me change this. I said this is going to be some random liquid. The mass of the liquid. So the force down is going to be equal to the mass of the liquid times gravity. And what is that mass of the liquid? Well, now I'll introduce you to a concept called density. And I think you understand what density is. It's kind of how much there is of zero, and that's a constant velocity. So it's not accelerating in any direction. So its net forces must be zero. Right? So this force down cylinder, I have I don't know, it's like a thin piece of foil or something that takes up the entire area of the cross-sectional area of the cylinder. And I did that just because I want that to be an indicator of whether the fluid is moving up or down or not. So let's say I have that in the fluid at some depth h, and since the fluid is completely static, nothing's moving, that object that's floating right at that level at a depth of h will also be static. And in order for something to be static, or it's not moving, what do we know about it? Well, we know that the net forces on it must be zero. In fact, that tells us that it's not accelerating. And obviously, if something's not moving, it has a velocity of zero, and that's a constant velocity. So it's not accelerating in any direction. So its net forces must be zero. Right? So this force down must be equal to the force up. Right? So what is the force down? What is the force down acting on this cylinder? Well, it's going to be the weight of the water above it, right? Because we're in a gravitational environment, and so this water has some mass, and so whatever that mass is times the gravitational constant will equal the force down. So let's figure out what that is. So force down, which is the same thing, is going to equal the mass of this water. Right? The mass of this water is going to equal the mass of that water times the gravitational constant. Oh, actually, I shouldn't say water. I'm using the let me change this. I said this is going to be some random the mass of the liquid. The force down is going to be equal to the mass of the liquid times gravity. And what is that mass of the liquid? Well, now I'll introduce you to a concept called density. And I think you understand what density is. It's kind of how much there is of something in a given amount of volume, how much mass per volume. And that's the definition of density. So, and the letter people use for density is rho. Let me do that into P for down. So rho, which looks like a P to me, that equals mass per volume. Mass per volume. And that's the density. So that the units are kilograms per meter cubed. That is density. And so, I think you might have an intuition of, if I have a cubic meter of lead, that is more, well, lead is more dense than, say, I don't know, marshmallows. And so because of that, if I have a cubic meter of lead, it will have a lot more mass and in a gravitational field weigh a lot more than a cubic meter of marshmallows. And of course, there's always that trick people say is, what weighs more, a pound of feathers or a pound of lead? But those obviously weigh the same. The key is the volume of a cubic meter of lead is going to weigh a lot more than a cubic meter of feathers. Well, anyway, making sure that we now know what the density is, let's go back to what we were doing before. So we said that the downward force is equal to the mass of the liquid times the gravitational force, right? And so what is the mass of the liquid? Well, we could use this formula right here. Density is equal to mass times volume. So we could also say that mass is equal to density times volume, right? I just multiply both sides of this equation times volume. So that's the volume. So in this situation, force down is equal to, let's substitute this with this. The mass of the liquid is equal to the density of the liquid times the volume of the liquid. I can get rid of these L's, times gravity. And what's the volume of the liquid? Well, the volume of the liquid is going to be the cross-sectional area of the cylinder, right? Times the height. So let's call this cross-sectional area A for area. That's the area of the cylinder or the foil that's floating within the water. So we get downward force is equal to the density of the fluid. I'll stop writing the L or the F, whatever I was doing there. The density of this liquid times the volume of the liquid. And the volume of the liquid is just the height times the area of the liquid. So that is just times the height times the area, and then times gravity. Times gravity. Fair enough. So we've now figured out, if we knew the density, this height, the cross-sectional area, and the gravitational constant, we would know the force coming down. But that's kind of vaguely interesting. But let's try to figure out what the pressure is, because that's what started this whole discussion. Is what is the pressure when you go to the deep parts of the ocean, etc. So this is the force. What is the pressure on this foil that I floated? Well, it's the force divided by the area of this foil, pressure of this foil. So I would take the force and divide it by the area, which is the same thing as A. So let's do that. So let's divide both sides of this equation by area. So the pressure coming down, that's P sub D. It sounds like a rapper's name. P sub D, the downward pressure at that point, is going to be equal to, and keep in mind, that's going to be the same thing as the upward pressure, right? Because the upward force is the same, and the area, when you're going upwards or downwards, is going to be the same thing. So the downward pressure is going to be equal to the downward force divided by area. It's going to be equal to this expression divided by area. So essentially, we can just get rid of the area here, right? So it equals P H A G divided by A. To get rid of the A's in both situations. So the downward pressure downward, is equal to the density of the fluid times the depth of the fluid, essentially, the height of the fluid above it, times the gravitational constant, PHG. And as I said, the downward pressure is equal to the upward pressure. And how do we know that? Because we know that the upward force is the same as the downward force. If the upward force were less, this little piece of foil would actually accelerate downwards. The fact that it's static, right? So it equals PHAG divided by A to get rid of A's in both situations. So the downward pressure downward, is equal to the density of the fluid times the depth of the fluid, essentially, the height of the fluid above it, times the gravitational constant, PHG. And as I said, the downward pressure is equal to the upward pressure. And how do we know that? Because we know that the upward force is the same as the downward force. If the upward force were less, this little piece of foil would actually accelerate downwards. The fact that it's static, it's in one place, lets us know that the upward force is equal to the downward force, and the upward pressure is equal to the downward pressure. So let's use that in an example. If I were on the same planet, and let's say this is water, and so the density of water, and this is something good to memorize, is 1,000 kilograms per meter cubed. 1,000 kilograms per meter cubed. So let's say the atmosphere, but I were to go, I don't know, 10 meters under the water, roughly 30 feet under the water. What would be the pressure on me? So my pressure would equal the density of water, 1,000 kilograms per meter cubed. Make sure your units are right. I'm running out of space, so units, times the height, 10 meters, times the gravitational acceleration, 9.8 meters per second squared. It's a good exercise for you to make sure the units work out. That's what 10,000 times 9.8. So the pressure is going to be equal to 98,000 pascals, which actually isn't that much. It just sounds like a lot. We'll actually see that this is almost 1 atmosphere, which is the pressure at sea level in France, I think. Anyway, I'll see you in the next video. That's what 10,000 times 9.8. So the pressure is going to be equal to 98,000 pascals, which actually isn't that much. It just sounds like a lot. We'll actually see that this is almost 1 atmosphere, which is the pressure at sea level in France, I think. Anyway, I'll see you in the next video. In the last video, we learned.
There you go. Good. Good job.
Learned that the pressure at some depth in the fluid is equal to the density of the fluid times how deep we are in the fluid, or kind of how high is the column of fluid above us, times gravity. Let's see if we can use that to solve a fairly typical problem you'll see in your physics class or even in AP physics class. So let's say that I have a bowl. And in that bowl, I have mercury. And then I also have this kind of inverted test tube that I stick in the middle of this is the side view. Let's say my test tube looks like this. Let's say I have no air in this test tube, there's a vacuum here. But the outside of this area here, this is exposed to the air. Now we're actually on Earth. We're actually in Paris, France at sea level, because that's kind of what an atmosphere is. In the last video, we learned that the pressure at some depth in a fluid is equal to the density of the fluid times how deep we are in the fluid, or kind of how high is the column of fluid above us, times gravity. Now let's see if we can use that to solve a fairly typical problem you'll see in your physics class or even on an AP physics test. So let's say that I have a bowl. Let me draw the bowl. And in that bowl, I have mercury. And then I also have this kind of inverted test tube that I stick in the middle of this is the side tube. Let's say my test tube looks something like this. Something like this. Let's say I have no air in this test tube, there's a vacuum here. But the outside of the bowl, this whole area out here, this is exposed to the air. Now we are actually on Earth. We're actually in Paris, France at sea level, because that's kind of what an atmosphere is defined as. So the atmospheric pressure, so essentially the way you can think about it, the weight of all of the air above us is pushing down on the surface of this bowl at 1 atmosphere. An atmosphere is just the pressure of all of the air above you at sea level in Paris, France. And in the bowl, I have mercury. Mercury is silver. Mercury.
Same.
I think I can recall. Okay, let me see. Let me try to use my filter. There you go. And let's say that mercury, there's no air in here. It actually is going to go up this column a little bit, and we're going to do the math as far as, well, one, we'll see why it's going up, and then we'll do the math to figure out how high does it go. So mercury goes up some distance. This is all still mercury. Mercury. It is actually how a barometer works. It's something that measures pressure. So you can imagine, and over here, at this part, above the mercury, but still within our little test tube, we have a vacuum. There is no air. Vacuum, one of my favorite words. It has 2 U's in a row. Anyway, so anyway, where was I? Oh, okay. So we have this set up. So my question to you is, how high is this column of mercury going to go? How high is it going to go? And first of all, let's just have the intuition as to why this thing is going up to begin with. So we have all this pressure from all of the air above us. And I know it's a little unintuitive for us because we're used to all of that pressure on our shoulders all of the time. So we don't really imagine it, but there is literally the weight of the atmosphere above us. And so that's going to be pushing down on the surface of the mercury on the outside of the test tube. And essentially, since there's no pressure here, the mercury is going to go up towards you. But now this state that I've drawn is a static state. We've assumed that all the motion is stopped, et cetera, et cetera, et cetera. So let's try to solve this problem. Oh, no, a couple of things we have to know before we do this problem. It's mercury, and we know that the mercury, the specific gravity, and I'm using terminology because a lot of these problems, the hardest part is the terminology. The specific gravity of mercury is 13.6. That's often a daunting statement on a test where you know how to do all the math and all of a sudden you know what is specific gravity. All specific gravity is the ratio of how dense that object is, that substance, to water. So all that means is that mercury is 13.6 times as dense as water, right? And hopefully after the last video, because I told you to, you should have memorized the density of water, is 1,000 kilograms per meter cubed. So the density of mercury, let's write that down. Density, that's the rho, P of mercury is going to be equal to 13.6 times the density of water. So times 1,000 kilograms per meter. Okay, so let's go back to the problem. So what we want to know is how high this column of mercury is. So we know that the pressure, let's consider this point right here. Let's consider this point right here, which is essentially the base of this column of mercury. What we're saying is the pressure on the base of this column of mercury right here, the pressure at this point down, pressure down has to be the same thing as the pressure up, right? Because the mercury isn't moving, we're in a static state. And we learned several videos ago that the pressure in is equal to the pressure out on a liquid system. So essentially, I have 1 atmosphere pushing down here on the outside of the surface. I must have 1 atmosphere pushing up here. So the pressure pushing up at this point right here, we can imagine that we have that aluminum foil there again. Just imagine that, where the pressure is hitting. The pressure there is 1 atmosphere. So the pressure down right here must be 1 atmosphere. And what's creating the pressure down right there? Well, it's essentially this column of water, or it's this formula, which we learned in the last video. So what we now know is that the density of the mercury times the height of the column of water times the acceleration of gravity on Earth, which is where we are, has to equal 1 atmosphere, because it has to offset the atmosphere that's pushing on the outside and pushing up here. So let's see. The density of mercury is this 13,600 kilogram meters per meter cubed. That's the density, times the height. We don't know what the height is, that's going to be in meters, times the acceleration of gravity, 9.8 meters per second squared, is going to be equal to 1 atmosphere. And now you're saying, Sal, this is strange. I've never seen this atmosphere before. We've talked a lot about it, but how does an atmosphere relate to pascals or newtons and all of that? So this is something else you should memorize. 1 atmosphere is equal to 103,000 pascals. And that also equals 103,000 newtons per meter squared, right? The 1 atmosphere is how much we're pushing down out here, so it's how much we're pushing up here, and that's going to be equal to the amount of pressure at this point from this column of mercury. And 1 atmosphere is exactly this much, equals 103,000 newtons per meters squared. So let's see, let's if we divide both sides, well, we could just do all of the math. So if we divide both sides by 13,609.8, we get the height is equal to 103,000 Newton per meter cubed over 13,600 kilograms per meter cubed times 9.8 meter per second squared. And what is that? And notice, make sure you always have the units right. That's the hardest thing about these problems, just to know that an atmosphere is 103,000 pascals, which is also the same as newtons per meter squared. Let's just do the math. So let me type this in. Let me just use 103,000 divided by 13,600 divided by 9.8 equals 0.77. We're dealing all with
Workout.
I is equal to
I work out.
0.77 meters. And you should see that the units actually work out. We have meters cubed in the denominator up here, we have meters cubed in the denominator down here, and then we have kilogram meters per second squared here, and then we have newtons up here. But what's a newton? A newton is kilogram meter squared per second. So when you divide, you have kilogram meter squared per second squared. Here you have kilogram meter per second squared. When you do all the division of the units, all you're left with is meters. So we have 0.77 meters, or roughly 77 centimeters, is how high this column of mercury is. And you can make a barometer out of it. You can say, oh, well, we make a little notch on this test tube, and that represents 1 atmosphere. And you can go around and figure out what the atmosphere, how many atmospheres, different parts of the globe. Anyway, I've run out of time. See you in the next video.
Why is he running out of time? Why is he running out of time? Why is everyone? Everybody has to be like below 10 minutes. Is that something? It's like a rule. So strange.
Let's say we have a cup of water. We draw the cup. So what's that? The bottom of the cup. And it's water. Well, let me say it's some liquid. It doesn't have to be water. Some arbitrary liquid. It could be water. So that's the surface of it. So we've already learned that the pressure at any point within this liquid is it's dependent on how deep we go into the liquid. And one point I want to make before we move on, and I touched on this a little bit before, is that the pressure at some point, it isn't just acting downwards, or it isn't just acting in one direction. It's acting in all directions on that point. So although how far we go down determines how much pressure there is, the pressure is actually acting in all directions, including up. And the reason why that makes sense is because I'm assuming that this is a static system, or that the fluids in this liquid are stationary, or even you can imagine an object down here, and it's stationary. And the fact that it's stationary tells us that the pressure in every direction must be equal. Especially, let's think about a molecule of water. A molecule of water, let's say it's roughly a sphere. If I have a molecule of water, let me put it in this corner, and then you can space it there. If the pressure were different in one direction, or let's say if the pressure down were greater than the pressure up, then the object would start accelerating downwards, right? Because its surface area pointing upwards is the same as the surface area pointing downwards. So the force upwards would be more, and it would start accelerating downwards. So even though the pressure is a function of how far down we go, at that point, the pressure is acting in every direction. So let's remember that. And now let's keep that in mind to learn a little bit about Archimedes' principle. So let's say I submerge a cube into this liquid. And let's say this cube, let me draw the cube up here. So let's say this cube has dimensions d. So every side is d. D, it's dimension d. So what I want to do is I want to figure out if there's any force, or what is the net force acting on this cube due to the water. Well, let's think about what the pressure on this cube is at different points. Well, at the depths along the side of the cube, we know that the pressure is equal, right? Because we know at this depth, say right here, the pressure is going to be the same as at that depth, and they're going to offset each other. So these are going to be the same. But one thing we do know, just based on the fact that pressure is a function of depth, is that at this point, the pressure is going to be higher, I don't know how much higher, than at this point, right? Because this point is deeper into the water. Mm-hmm. So let's call this P1. That's the pressure on, let's call it pressure on top, PT. Let's call this point down here, let's call that PD. Pressure on the bottom, PP. Right? And what's going to be the net force on this object, on this cube? Well, it's going to be the net force, or F sub n, is going to be equal to the force acting upwards on this object. And what's the force acting upwards on the object? It's going to be this pressure at the bottom of the object, times the surface area at the bottom of the object? Well, what's the surface area at the bottom of the object? Well, that's just d squared, right? Any surface of a cube is d squared, so the bottom is going to be d squared. And then minus, and I'm doing this because I actually we know that the pressure down here is higher than the pressure here, so this is going to be the larger quantity, and that the net force is actually going to be upwards. So that's why I can do minus confidently up here. Minus the pressure at the top. So what's the force at the top? The force at the top is going to be the pressure on the top times the surface area of the top of the cube, right? Times d squared. Then we can even separate out the d squared already at that point. So the net force is equal to pressure at the bottom minus the pressure at the top, or the difference in pressure, times the surface area of either the top or the bottom, or really any of the sides of the cube. Now let's see if we can figure out what these are. Let's say the cube is submerged h units or h meters into the water. H. So what's the pressure at the top? So the pressure at the top is going to be equal to the density of the liquid, which I keep saying water, but it could be any liquid. The density of the liquid times how far down we are. So we're h units down, maybe h meters, times gravity. And what's the pressure at the bottom? Well, the pressure at the bottom is going to be the density of the liquid times the depth. So what's the depth? It would be this h, and then we're another d down, right? So h plus d, that's our total depth, times gravity. Right? So let's just substitute both back into our net force. Let me switch colors to keep from getting numbness. So I get the net force is equal to the pressure at the bottom, which is this. Let's just multiply it out so we get p times h times g, p h g plus d times p times g, d p g. I just distributed this. I multiply this out. That's the pressure at the bottom. And then minus the pressure at the top, minus p h g, and then we learn all of that times d squared. Right? So immediately we see something cancels out. PhD, subtract, cancels out. So we're just left with what's the net force? The net force is equal to dpg times d squared, or that equals d cubed times the density of the liquid times gravity. Well, let me ask you a question. What is d cubed? D cubed is the volume of this cube, right? Well, what else is it? Well, it's also the volume of the water displaced, right? If I stick this cube into the water, and the cube isn't drinking or anything, that, and then you can imagine being empty, but that amount of water has to be moved out of the way in order for that cube to go in, right? So this is the volume of the water displaced. Volume, it's also the volume of the cube. Volume of water displaced. This is the density. I keep saying water, but let's just say it's water, but it could be any liquid. This is the density of the liquid. This is gravity. So what is this? Volume times density is the mass of the liquid displaced, right? So the net force is also equal to the mass of liquid displaced. So let's just say mass times gravity. Or, because the net force acting on this object is, what's the mass of the liquid displaced times gravity? That's just the weight of
in the room?
Of liquid displaced. So that's a pretty interesting thing. So if I submerge anything, the net force acting upwards on it, or the amount that I'm lighter by, is equal to the weight of the water being displaced. And that's actually called Archimedes' principle. And that net upward force, due to the fact that there's more pressure on the bottom than there's on the top, that's called the buoyant force. And that's what makes things float. So I'll leave you there with right now, just to ponder that. And we'll use this concept in the next couple of videos to actually solve some problems. I'll see you soon. Say that I have some object, and when it's outside of water, its weight is, so weight outside of water is, 10 newtons. Let's say when I submerged water, I put it on a weighing machine in water. Its weight, let's call it weight in water, is, it's 2 newtons. So what must be going on here? Well, the water must be exerting some type of upward force to counteract at least 8 newtons of the person's virtue. Not the person, the object's originally is to be a very small person. People's weights in newtons are in hundreds. But anyway, and that difference is the buoyant force, right? So the way to think about it is, once you put the object in the water, since it could be a cube, it doesn't have to be a cube, it could be anything. It's in the water. So it's the water up here. We know that there's a downward weight, right? That is 10 newtons. But we know that once it's in the water, the net weight is 2 newtons. So there must be some force acting upwards on the object of 8 newtons, right? And that's the buoyant force that we learned about in the previous video. The video about that makes sense. This is the buoyant force. So the buoyant force is equal to 10 minus 2 is equal to 8, right? That's how much the water is pushing up. And what is that also equal to? That equals the volume, the weight of the water displaced. So 8 newtons is equal to weight of water displaced. And what is the weight of the water displaced? That's the volume of the water displaced times the density of water times gravity. Right? So what is the volume of water displaced? Well, it's just the volume of water by 8 newtons by the density of water is 1,000 kilograms per meter cubed. This 8 newtons. So a newton is what? Kilogram meter per second squared. And then the gravity is 8 meter per second squared. And if we look at all the units, they actually do turn out with just, you end up having just meters cubed. But let's do the maths. Equals 8.2 times 10 to the minus 4 meters, cubic meters. So just knowing the difference in the weight of an object, I can figure out the difference when I put it in water. I can figure out the volume. And so this would be a fun game to do next time your friends come over: is weigh yourself outside of water, then some kind of string or a waterproof weighing machine, put it at the bottom of your pool, stand on it, and figure out what your weight is. Assuming that you're dense enough to go all day in water, you can figure out somehow your weight in water, and then you would know your volume. There's other ways. You can just figure out how much the water increases and take that water weight. Anyway, this was interesting. Just knowing how much the buoyant force of the water was, or how much lighter we are when the object goes in the water, we can figure out the volume of the object. And this might seem like a very small volume. Just keep in mind, in a meter cubed, you have, let's see, you have 27 square feet, right?
27 square feet. So we multiply that number times 27. It equals 0.02 square feet, roughly. And 0.02 square feet, how many, in a square foot, there's actually 12 third power times 12 is equal to 1728 times 0.02. So this is actually 34 square inches. So the object isn't as small as you may have thought it would be. It's actually, it's like maybe a little bit bigger than 3 inches by 3 inches by 3 inches. So it's a reasonably sized object. Anyway, let's do another problem. Let's say I have some balsa wood, and I know that the density of balsa wood is 130 kilograms per meter cubed. What's the density of balsa wood? I have some big cube of balsa wood. What I want to know is if I put that on a drop of water, that's the water, and I have some big cube of balsa wood on the ground, big cube of balsa wood, the water's on top of it, you see it submerged in water. I want to know what percentage of the cube goes below the surface of the water. Interesting question. So how do we do that? Well, for the object to be at rest, for this big cube to be at rest, there must be zero net forces on this object, right? So in that situation, the buoyant force must completely equal the weight, or the force of gravity. What's the force of gravity going to be? The force of gravity is just the weight of the object, and that's the volume of, let's just say, the wood, volume of balsa wood, times the density of the balsa wood, times the density of balsa wood, times gravity. And what's the buoyant force? The buoyant force is equal to the volume of the displaced water, right? Volume of displaced water, but that's also, well, it's the volume of displaced water, and it's the volume of the cube that's been submerged. So part of the cube that's submerged, that's volume, that's also equal to the amount of volume of the water displaced, right? You can say that's the volume of the water submerged, which is the same thing, remember, as the volume of the water displaced, times the density of water, times gravity, or the density of water. Remember, the buoyant force is just equal to the weight of the water displaced, and that's just the volume of the water displaced, times the density of water, times gravity, equals the volume of the water displaced. It's the exact same thing as the volume of the block that's actually submerged. And since the block is stationary, it's not accelerating upwards or downwards, we know that these two quantities must equal each other. So the volume of the wood, the entire volume, not just the amount submerged, times the density of the wood, times gravity, must equal the volume of the wood submerged, which is equal to the volume of the water displaced, times the density of water, times gravity. We have the acceleration of gravity, we have that on both sides, so we cross it out, so we call this easy monopoly. And then let's see what happens if we divide both sides by volume of the balsa wood. We get, let's see again. Let's divide both, I'm sure you can figure it out. You can get, divide both sides by that volume submerged, divided by the volume of the balsa wood. Right, I just divide both sides by dV and quantity of sides is equal to the density of the balsa wood divided by the density of water. That makes sense. I just did quick algebraic operations, but hopefully that makes sense to you. And now we're ready to solve our problem. Because my original question is what percentage of the object is submerged. So that's exactly this number, right? If we say, but this is the volume submerged over the total volume, this is the percent submerged. So that equals the density of balsa wood, which is 130 kilograms per meter cubed, divided by the density of water, which is 1,000 kilograms per meter cubed. So 130 divided by 1,000 is 0.13. So VS UV is equal to 0.13, which is 13%. So exactly 13% of this object will be, of this balsa wood block, will be submerged in the water. That's pretty easy. It actually didn't have to be a block. It could have been shaped like a horse. I'll see you in the next video.
What does specific gravity mean? The specific gravity of an object is the density of that object divided by the density of water. The density of water is 1,000 kilograms per meter cubed. For instance, the density of gold is 19,300 kilograms per meter cubed, so the specific gravity of gold is 19.3. The density of ketchup is 1,400 kilograms per meter cubed, so the specific gravity of ketchup is 1.4. Note, there's no units for specific gravity because it's the ratio of one density to another density, so the units cancel each other out. Okay, so why even bother defining something called the specific gravity? Well, one really cool thing about specific gravity is that for something that floats, the specific gravity tells you the fraction of that object that will be below the water while it's floating. For instance, say you let a cube of wood with specific gravity 0.2 float in water. Since the specific gravity is 0.2, that means that 20% of the total volume of this wood is going to be submerged below the water while it's floating. If the cube of wood had a specific gravity of 0.6, 60% of the wood would be submerged beneath the water's surface. Ice has a density of about 920 kilograms per meter cubed. That means ice has a specific gravity of 0.92. And that's why 92% of an iceberg's volume is actually underneath the water. But what if we were to use a cube that had a density of 2,700 kilograms per meter cubed? The specific gravity would be 2.7, which means that 270% of this cube would be submerged beneath the water. But you can't have more than 100% of an object submerged. Even if the object were to sink, the maximum amount submerged would be 100%. So if the specific gravity of an object is greater than 1, that object is going to sink if placed freely in water. and it'll have exactly 100% of its volume submerged. Usually, when people are referring to the specific gravity, they're referring to the density of the object divided by the density of water. But sometimes it's useful to define the specific gravity with respect to a liquid that's different from water. For instance, if you were to let some wood of density 638 kilograms per meter cubed float in oil that has a density of 850 kilograms per meter cubed, you could still find the percent of the wood that's submerged underneath the oil. Just use the density of oil instead of the density of water in the specific gravity formula. If we do that, we'll find that the wood does float in this oil with 75% of the wood's volume submerged beneath the surface of the oil.
Fluid simulation. Gases, can make molecular gases. We'll have to do tomorrow because we'll have to wake up tomorrow. I have a lot to do tomorrow. Alright, everyone. Thanks for watching. Have a great day. See you guys tomorrow.